For the past few weeks, every astronomer on Earth, from backyard observers to the teams behind the Hubble Space Telescope and the James Webb Space Telescope, has been buzzing about a single object, not because it is bright, not because it is beautiful, but because 3i Atlas is doing something no comet has ever done, something that, according to our own physics, should be impossible. In the span of just 9 days, 2 independent observations, taken by completely different telescopes on opposite sides of the observing world, have produced a contradiction so massive and so mathematically violent that astrophysicists are running out of ways to explain it. One observation shows jets blasting millions of kilometers into space, jets powerful enough to eject more mass than the comet even contains. The other observation shows a crystal clear set of images with a perfectly normal, intact nucleus, with none of the debris, none of the fragments, and none of the chaos that physics says must exist. This is not a debate. This is not speculation. This is a direct collision between observation and physics, between what we saw and what we know. And right now, the world of astronomy is split down the middle trying to reconcile it. So before we go deeper, before we break down the calculations, the energy budget, the thermal physics, and the impossible absence of 50 billion tons of missing mass, take a second to support this investigation. Hit the like button if you care about real science getting real attention. And subscribe, because in the next few weeks, telescopes across 6 continents are going to make or break this mystery, and you are going to want to see exactly what they find. Now, let us start with the observation that made everyone realize something was wrong. On the 9th of November 2025, Frank Niebling and Michael Buechner captured stacked exposures of 3i Atlas showing 2 distinct jet structures, an anti-tail jet pointing toward the Sun, extending approximately 950,000 kilometers, which we will round to 1 million kilometers for the calculation, and a main tail jet pointing away from the Sun, extending roughly 2,850,000 kilometers, which we will round to 3 million kilometers. These measurements come from analyzing the photographs with astrometric software. You measure the angular size of the jets in the image, you know the distance to the comet, and simple trigonometry gives you the physical size. Distance to 3i Atlas on the 9th of November was approximately 2 astronomical units, which is about 300 million kilometers from Earth. The angular measurements and the distance calculations are not controversial. Multiple observers have confirmed these jet sizes. So we have jets, big jets, jets spanning millions of kilometers. Before we can understand what is missing, we need to understand the mathematics that says something should be there. This is not optional. The numbers are the foundation of everything that follows. I am going to walk through the calculation that Avi Loeb published, not simplified, not made childish. The actual physics, step by step, with every assumption laid out so you can judge for yourself whether it makes sense. If you find yourself getting lost in the mathematics, stay with me. It builds towards something important, and unlike a lot of science communication that says, trust us, here is the conclusion, I am going to show you exactly how we get there. Start with what we can see, what is not in dispute. For a natural comet, material leaves the surface through sublimation. Solid ice turns directly into gas when it is heated by sunlight. This gas expands away from the nucleus and carries dust particles with it. The velocity of this outflowing gas is determined by temperature. More specifically, it is approximately equal to the speed of sound in that gas at that temperature. The formula for the speed of sound in a gas can be written in words as follows. The velocity is equal to the square root of gamma multiplied by r multiplied by t, all divided by m. In this formula, gamma is the heat capacity ratio. For carbon dioxide, gamma is about 1.3. R is the universal gas constant, which is about 8.314 joules per mole per Kelvin. T is the temperature measured in Kelvin. M is the molecular mass. For carbon dioxide, the molecular mass is 44 grams per mole. At the distance of 3i Atlas from the Sun during this period, about 1.5 to 1.7 astronomical units, the surface temperature of sublimating carbon dioxide ice is approximately 195 Kelvin, which is about minus 78 degrees Celsius. If you plug these numbers into the sound speed formula, you get a velocity of roughly 440 meters per second, which is about 0.44 kilometers per second. This is consistent with observations of other comets at similar distances from the Sun. Water ice at the distance of Earth from the Sun produces outflow velocities around 0.8 to 1.0 kilometers per second. Carbon dioxide, being lighter and sublimating at lower temperatures, produces slightly slower velocities. So the outflow velocity is about 0.4 kilometers per second, and we will use this rounded number. Now, if material is flowing at roughly 0.4 kilometers per second, and we observe it extending to 1 million kilometers, how long has it been flowing? In simple terms, the time is equal to the distance divided by the velocity. For the sunward jet, the 1 million kilometer jet, the time works out to about 2,500,000 seconds, which is roughly 29 days. For the anti-sunward jet, the 3 million kilometer jet, the time works out to about 7,500,000 seconds, which is roughly 87 days. So these jets must have been flowing for approximately 1 to 3 months to reach their observed sizes. Not brief outbursts, not transient phenomena, sustained, continuous outgassing for weeks to months. This is important because it means we are not talking about a momentary spike in activity. We are talking about prolonged mass loss over an extended period around perihelion. Now comes the clever part of Arvey-Loeb's analysis. The sunward jet, the anti-tail, is pointing toward the Sunday. That is unusual. Normal comet tails point away from the sun because solar radiation pressure and the solar wind push material outward, but this jet is clearly visible pointing toward the sun in the photographs. How is that possible? The jet must be flowing outward from the comet with enough momentum that it can push back against the solar wind, at least for a while, before being stopped and turned around. And we can see where it is stopped, at approximately 1 million kilometers from the nucleus. This gives us crucial information. The solar wind at the location of 3I Atlas is flowing at approximately 400 kilometers per second. This value is measured directly by spacecraft and is well established. The solar wind consists of charged particles, mostly protons, with a density of about 2 to 3 protons per cubic centimeter at this distance. When two streams of material collide, they push against each other with a force known as ram pressure. Ram pressure depends on two things: the density of the material and the square of its velocity. So let us start with the solar wind. The solar wind has a density of roughly 3 protons per cubic centimeter. If you convert that into mass, that becomes about 5 times 10 to the power of negative 21 kilograms per cubic centimeter. The speed of the solar wind at the distance of 3I Atlas is about 400 kilometers per second. In centimeters per second, that is 4 times 10 to the power of 7. When you multiply the density by the square of that speed, the resulting ram pressure is roughly 8 times 10 to the power of negative 6 dyne per square centimeter. Now, for the comet's jet to stop the solar wind at a distance of about 1 million kilometers from the nucleus, the jet must push back with an equal amount of ram pressure. In other words, the ram pressure of the jet must match the ram pressure of the solar wind. We already know the velocity of the jet. It is about 0.4 kilometers per second, which is 4 times 10 to the power of 4 centimeters per second. That is roughly 1,000 times slower than the solar wind. Because ram pressure depends on velocity squared, we can calculate the jet's density by comparing these two speeds. You take the solar wind density, about 5 times 10 to the power of negative 21 kilograms per cubic centimeter, and multiply it by the square of the ratio between the solar wind speed and the jet speed. The ratio of speeds is 1,000. 1,000 squared is 1 million. Multiply the solar wind density by 1 million, and you get a jet density of about 5 times 10 to the power of negative 15 kilograms per cubic centimeter. If you express that in proton masses, it becomes roughly 3 million proton masses in each cubic centimeter of the jet. That means the jet is about 1 million times denser than the solar wind. This number is the key to the entire calculation, because now we can compute the mass flow rate, sometimes called the mass flux. Mass flux is the rate at which mass moves through a given area. It depends on 3 things: the density of the material, the velocity of the material, and the cross-sectional area of the jet. For the jet coming from 3I Atlas, we now have a density of roughly 5 times 10 to the power of negative 15 kilograms per cubic centimeter, a velocity of 0.4 kilometers per second, and all that remains is to second, determine the cross-sectional area of the jet. Now we need the final ingredient, the cross-sectional area of the jet. When you look at the November 9th images, the jets are not thin lines. They have real width. The sunward jet, the anti-tail, appears to be at least 100,000 to 200,000 kilometers wide, where it meets the boundary with the solar wind. So let us be extremely conservative. Let us assume the jet has a square cross-section roughly 1 million kilometers on each side. This is actually smaller than what the images suggest, but we will deliberately underestimate it. 1 million kilometers by 1 million kilometers gives an area of 1 million square kilometers. If we convert that into square centimeters, it becomes roughly 10 to the power of 26 square centimeters. Now we can compute the mass flow through that area. We already have a density of about 5 times 10 to the power of negative 15 kilograms per cubic centimeter, velocity of 4 times 10 to the power of 4 centimeters per second, and an area of 10 to the power of 26 square centimeters. Multiply these together, and the mass flux, the mass per second flowing through the jet, comes out to roughly 2 times 10 to the power of 16 kilograms every second. In simpler terms, that is about 2 million kilograms per second. Now ask the obvious question. How much mass is that over the course of 1 month? 1 month contains about 2.6 million seconds. Multiply the mass per second by the number of seconds in a month, and the total mass comes out to roughly 5 times 10 to the power of 13 kilograms. That is about 50 billion kilograms. Or, said more clearly, 50 billion metric tons. If we stay even more conservative and use only the sunward jet, with an area closer to 1 million square kilometers, the total mass loss comes out to roughly 5 billion tons per month. That is where the 5 billion tons figure originates. And if you include the much larger anti-solar jet, the main tail, and the full area that appears to be active, the number climbs closer to 50 billion tons. Now comes the part that makes scientists uncomfortable. If 3I Atlas really is losing between 5 and 50 billion tons through ordinary sublimation, where is the energy coming from? Sublimating carbon dioxide ice requires about 600 joules for every gram. To sublimate 5 billion tons of carbon dioxide ice in the span of a single month, the comet would need an enormous amount of energy. Let us calculate it in simple, spoken terms. 5 billion tons is the same as 5 times 10 to the power of 12 kilograms. Sublimating 1 gram of carbon dioxide ice requires about 600 joules of energy. There are 1,000 grams in a kilogram. So when you multiply it all out, the total energy needed comes to roughly 3 times 10 to the power of 18 joules. Where could that energy possibly come from? The only realistic source is the Sunday. At the comet's distance during perihelion, about 1.36 astronomical units, the solar energy that hits 1 square meter every second is roughly 700 joules. 1 month contains about 2.6 million seconds. Multiply that by the solar flux, and each square meter receives about 1.8 billion joules over the course of the month. Now we ask the crucial question, how much absorbing surface area would the comet need in order to collect the total energy required? If the comet must gather 3 times 10 to the power of 18 joules, and each square meter can only absorb 1.8 billion joules in a month, the comet would need roughly 1.7 billion square meters of active surface. That is the same as about 1,700 square kilometers. And if you convert that surface area into the diameter of a sphere, you get a sphere roughly 23 kilometers across. But here is the problem. Hubble Space Telescope measured the maximum diameter of 3I Atlas at only 5.6 kilometers. In other words, the comet would need to be at least 4 times larger in diameter just to absorb enough sunlight to sublimate 5 billion tons of ice. And if the true mass loss is closer to 50 billion tons, which is what you get when you include the main tail and the full jet area, then the required diameter jumps to about 50 kilometers. That is nearly 10 times larger than what Hubble observed. Scientists have tried to escape this mathematical trap by proposing several explanations, but every one of them runs into a wall. Hypothesis 1. The comet is bigger than we think. Maybe Hubble's size estimate is wrong. Size estimates depend on albedo, how reflective the surface is. If the comet were much darker than assumed, it could be larger, but Hubble's measurement comes from direct imaging. The comet appears as a point source, with a specific brightness. Unless the comet is essentially pitch black, darker than charcoal, the size constraint still holds. Hypothesis 2. The outflow velocity is higher. Maybe the gas is not moving at 0.4 kilometers per second. Maybe it is moving much faster. Faster gas would mean the jets could reach their enormous length in less time, which would reduce the total mass lost. But the outflow velocity is set by temperature, and the temperature is set by sunlight. You cannot heat the gas far beyond that limit without breaking the laws of thermodynamics. Hypothesis 3. The jets are narrowly focused. Maybe the jets are extremely thin, like pencil beams, so the cross-sectional area is far smaller than we estimated. A smaller area would reduce the mass flow, but the photographs tell a different story. The jets are broad, diffuse, and wide. These are not laser beams. Hypothesis 4. The density is lower. Maybe our ram pressure calculation is off. Maybe the jet is less dense than we think. But the ram pressure calculation is standard fluid dynamics. For the jet to stop the solar wind 1 million kilometers from the nucleus, the density must be roughly what we computed. There is no way around it. Hypothesis 5. Something else caused the acceleration. Maybe the non-gravitational acceleration observed by NASA's Jet Propulsion Laboratory was not caused by outgassing at all. Maybe the comet was being pushed by something else. But what? What could apply a sustained, measurable force over several weeks? We will come back to this idea later. Hypothesis 6. The comet's mass was underestimated. Maybe 3I Atlas is much heavier than the current estimate of 33 billion tons. If the total mass were 10 times larger, then losing 5 to 50 billion tons might not be catastrophic, but that mass estimate comes from the absence of non-gravitational acceleration before October. If the comet were 10 times more massive, the same amount of outgassing would have produced far less acceleration, and we would still be facing the same contradiction. The numbers would simply scale upward. The problem would not disappear. Every conventional explanation collapses under its own weight. The mathematics behind this is ironclad. If the jets are real, and they are, because we have clear photographic evidence, and if those jets were produced by normal cometary outgassing, then the mass loss must have occurred. But the debris that should exist from that mass loss simply is not there, at least not in the images taken on November 11th. This is why Avi Loeb refers to the situation as an anomaly, not because he is jumping to wild conclusions, but because the numbers refuse to line up with conventional comet physics. Something is wrong. Either we are overlooking something enormous in the observations, or our understanding of comet physics is incomplete, or something entirely different is happening. Before we can explore those possibilities, we need to answer a simple question. If 3I Atlas really lost that much mass, what should the aftermath look like? This isn't guesswork. We have real, historical examples of comets that shed massive amounts of material. We know exactly how they behave when they fragment, when they disintegrate, and even when they explode. And every time, the debris is obvious. So let us walk through 3 real cases that define the baseline for comet destruction. Case Study 1. Comet Linear Complete Disintegration. In the month of July, in the year 2000, something catastrophic happened to Comet Linear. As it approached the Sun, the nucleus began to fracture, not into a few pieces, but into dozens, and possibly even hundreds of fragments. The Hubble Space Telescope captured the event in detail. It recorded at least 60 distinct pieces drifting away from one another. Each fragment formed its own small coma, and the pieces stretched out along the orbit, creating a debris train hundreds of thousands of kilometers long. Spectroscopic measurements showed the comet was releasing about 2,000 kilograms of water vapor every second at peak activity. During the single week in which the fragmentation unfolded, Comet Linear lost roughly 100 million tons of material. possibly 20 to 30% of its entire mass. So what did this look like from Earth? Even observers using modest 8 to 12-inch telescopes could easily see a rapidly expanding coma, swelling from 100,000 kilometers to more than 500,000 kilometers in just a few days. Multiple bright condensations, each one marking a separate fragment surrounded by its own mini-coma. A broad diffuse tail extending more than 1 million kilometers. A dramatic increase in brightness. The comet jumped from magnitude 11 to magnitude 6, bright enough to be seen clearly in binoculars. The debris was obvious, unmistakable. There was no way to look at Comet Linear after this event and think it was an intact, ordinary comet. Total mass lost, roughly 100 million tons. Observable debris, enormous, unmistakable, and recorded by hundreds of observers. Now compare this to the calculated mass loss for 3I Atlas, between 5 billion and 50 billion tons. That is 50 to 500 times more mass than Comet Linear lost. So if 100 million tons produced such dramatic, obvious destruction, what should 50 billion tons look like? Case Study 2, Comet Schwarzmann-Wachmann. 3. The fragmentation event. Comet Schwarzmann-Wachmann 3 first broke apart in the year 1995. By the time it returned in 2006, during a close approach to Earth, the breakup had become dramatic. The comet was no longer a single object. It had separated into more than 60 individual pieces, labelled Fragment A, Fragment B, Fragment C, and so on. The Spitzer space. Telescope observed these fragments in infrared light. It measured enormous dust production rates. Fragment C alone was releasing roughly 30,000 kilograms of dust every second at peak activity. When astronomers combined the activity of all 60 fragments, they estimated that several 100 million tons of material were lost during that 2006 apparition. So what did this look like from Earth? Even amateur astronomers using simple 6-inch telescopes could clearly see individual fragments spaced hundreds of thousands of kilometers apart, each fragment surrounded by its own small coma. Dust tails from the larger fragments stretching more than 2 million kilometers. The entire chain of fragments strung out along the comet's orbit like pearls on a string. A combined coma structure more than 3 million kilometers across when all the fragments were included. The breakup was so obvious, so dramatic, that it became a major target for public million observing. Thousands of amateur astronomers photographed it. Anyone who pointed a small telescope at the object could instantly tell it was not a normal, intact comet. Total mass lost, roughly 500 million tons. Observable debris, many fragments, enormous coma structures, and dust tails millions of kilometers long. And once again, 3I Atlas is supposed to have lost 10 to 100 times more mass than this. Case Study 3, Comet Ison, the perihelion destruction. Comet Ison was supposed to be the comet of the century, and for a moment it looked like it might live up to that title. But on November 28, 2013, everything changed. As Ison approached the Sun, it came incredibly close, only about 1.8 million kilometers above the solar surface. At that distance, the heat and tidal forces were extreme. SOHO and Stereo spacecraft watched the entire event unfold in real time. As the comet neared the Sun, it brightened dramatically. This surge in brightness meant one thing: enormous amounts of material were turning directly into gas. Estimates suggest the comet was shedding over 100,000 kilograms of material every second. And then, during the moment of closest approach, Ison essentially vaporized. It did not survive perihelion. It did not emerge on the far side as a solid, intact nucleus. Instead, observers saw exactly what happens when a comet truly dies: a broad, diffuse cloud of debris where the nucleus should have been, a rapid collapse in brightness, and within just a few days, nothing left except a faint, fading smear of dust. The total mass lost was enormous, the entire nucleus, estimated at between 2 and 3 billion tons. And even though Ison was positioned extremely close to the Sun and difficult to observe from Earth, spacecraft still clearly recorded a massive, expanding debris cloud, dust spreading out over millions of kilometers, gas production plummeting to almost nothing, as the ice supply vanished. And most importantly, the total absence of any solid nucleus. When a comet loses billions of tons of material, the signs are not subtle. They are dramatic, they are unmistakable, and they are impossible to confuse with an intact, healthy comet. Let us compare these comets directly. First, Comet Linear in the year 2000. It lost around 100 million tons of material. The result was unmistakable. More than 60 fragments, a coma 500,000 kilometers across, and a brightness easily visible in binoculars. Next, Comet Schwarzmann-Wachmann 3 in 2006. It shed roughly 500 million tons. Observers saw over 60 fragments spread across millions of kilometers, with multiple dust tails and a brightness of magnitude 5 to 7. Then, Comet Ison in 2013. It lost between 2 and 3 billion tons, the entire nucleus. Spacecraft recorded a huge, expanding cloud of debris and the complete disappearance of any solid core. And finally, 3I Atlas. Based on the calculated jet densities and durations, the numbers point to a mass loss between 5 billion and 50 billion tons. Yet the observations show something very different. A single, intact nucleus, a modest coma around 100,000 kilometers across, and a faint brightness around magnitude 11 or 12. 3I Atlas appears quieter and more stable than comets that lost a few 100 million tons, and far quieter than comets that lost a few billion. The behavior does not match the expected outcome. Based on every historical example we have, the debris from 3I Atlas should look like this, for a mass loss of roughly 5 billion tons. If the comet fragmented, we would expect 50 to 100 distinct pieces, easily visible in Hubble images. If it stayed intact but was heavily sublimating, the coma should be 1 to 2 million kilometers in diameter. Gas production should reach 10,000 kilograms per second, measurable in spectroscopy. The dust tail should stretch at least 3 million kilometers, visible even in modest telescopes. And the comet's brightness should be around magnitude 8 or 9, visible in good binoculars. For a mass loss closer to 50 billion tons, fragmentation should produce hundreds of pieces, forming a debris field more than 5 million kilometers across. If the nucleus somehow remained intact, which is physically impossible, at that level of mass loss gas production would exceed 100,000 kilograms per second. The coma would expand to between 5 and 10 million kilometers. The tail would reach more than 10 million kilometers, and the comet would brighten to magnitude 6 or 7, visible to the naked eye. But here is what was actually observed on November 11th. Fragmentation, none. A single intact nucleus. Coma diameter, roughly 1 dockham, 100,000 to 200,000 kilometers. Gas production, around 500 to 1,000 kilograms per second. Tail, modest, only a few 100,000 kilometers long. Magnitude, 11 to 12, requiring an 8-inch to 12-inch telescope. The discrepancy is staggering. Every historical example of major cometary mass loss shows dramatic, unmistakable consequences. Multiple fragments, enormous comas, long and bright dust tails, and a sharp rise in brightness that makes the comet easy to observe. 3I Atlas shows none of this. Its appearance is consistent with a comet that lost perhaps 0.1% to 1% of its mass, a few 100 million tons at most, not 5 billion, and certainly not 50 billion. Some scientists have suggested a possible escape hatch. Maybe 3I Atlas has an extremely low dust-to-gas ratio. Maybe it is releasing enormous amounts of gas, but very little dust. Gas is transparent, so we would not see it directly except in spectroscopy. It is a reasonable idea, so let us examine it. Typical comets have dust-to-gas ratios between 0.1 and 1. That means for every kilogram of gas, they release between 0.1 and 1 kilogram of dust. If 3I Atlas had a very low ratio, something like 0.01 rare, but still within the realm of possibility, then 5 billion tons of gas would still produce 50 million tons of dust. 50 billion tons of gas would still produce 500 million tons of dust. 50 to 500 million tons of dust is enormous. That much dust would be comparable to what comet Linear released, and Linear was obvious even in modest backyard telescopes. For the dust to remain invisible, the dust-to-gas ratio would need to drop to around 0.001 or lower, essentially a dust-free comet. Such ratios have never been observed. Carbon dioxide ice contains dust, grains, and sublimation. Naturally carries those grains outward. You cannot have massive CO2 outgassing without releasing at least some dust along with it. And remember, we are not only talking about dust, we are talking about 5 to 50 billion tons of gas. Even transparent gas still scatters light. It still absorbs energy. It still produces emission lines in spectroscopy. We know this because on August 6, 2025, well before perihelion, the James Webb Space Telescope observed 3I Atlas and measured carbon dioxide production at roughly 150 kilograms per second. If that carbon dioxide production rate increased by a factor of 100 at perihelion, which is a normal response to stronger solar heating, the rate would climb to around 15,000 kilograms per second. But to reach 5 billion tons of mass loss in a single month, the comet would need to produce 2 million kilograms per second. That is more than 10,000 times the pre-perihelion rate. Has any comet in history ever increased its gas production by a factor of 10,000 near perihelion? No. A 10-fold increase is common. A 100-fold increase is high, but still reasonable. A 1,000-fold increase would be extraordinary. 10,000-fold is unprecedented. And this leads us to a crucial test, one that the December observations will perform. Spectroscopy measures the strength of emission lines, and those intensities are directly proportional to the gas production rate. So if 3I Atlas really lost between 5 and 50 billion tons of carbon dioxide, spectroscopy must detect the following. For 5 billion tons over 1 month, carbon dioxide production around 2 million kilograms per second, infrared emission lines bright enough for the James Webb Telescope to detect easily, water production above 100,000 kilograms per second, based on Webb's earlier measurement that the comet is at least 4% water, strong hydroxyl emission in ultraviolet, which Hubble can detect without difficulty. For 50 billion tons, carbon dioxide production around 20 million kilograms per second. This would be one of the highest gas production rates ever measured for any comet. Spectroscopic lines so bright they would literally saturate instruments P6 unless exposure times were adjusted. Now consider the alternative. What if December spectroscopy measures production rates of only 1,000 to 10,000 kilograms per second? That amount of gas could produce perhaps 50 to 500 million tons over a month. Not 5 billion, not 50 billion. And that is the nightmare scenario for conventional comet physics. Because it would mean 3 things. 1, the jets are real. 2, the mass loss calculation is correct. 3, the physical evidence of that mass loss simply is not there, which leaves only a few possibilities. The jets were not formed by normal sublimation, or something is hiding or removing the debris, or our understanding of comet behavior is fundamentally incomplete. There is another way to test the mass loss hypothesis. Look for fragments. If 3I Atlas really lost between 15 and 50% of its total mass in a short period of time, the nucleus should not still be intact. Natural comet nuclei are rubble piles. They are loose collections of ice, dust, and rock, held together only by weak gravity and by frozen volatiles acting as glue. When you heat a rubble pile quickly and unevenly, enormous stress builds up. The sunlit side warms faster than the shadowed side. Different materials expand at different rates. Ice sublimates from one region faster than another. All of this creates internal strain that weakens the structure. Historically, comets that lose more than 10% of their mass near perihelion almost always break apart. Avi Loeb calculated that for 3I Atlas to expose enough surface area to sublimate 50 billion tons using only sunlight, the nucleus would need to shatter into at least 16 equal pieces, and very likely far more. So the obvious question is, where are those pieces? The Hubble Space Telescope has enough resolution to detect fragments separated by at least 1,000 kilometers. At the current distance of 3I Atlas, about 270 million kilometers on December 19th, Hubble can resolve structures roughly 500 to 1,000 kilometers across. If the nucleus fragmented into 16 or more pieces, And if those pieces drifted apart by even 5,000 to 10,000 kilometers, which would naturally happen within just a few days because each fragment would follow a slightly different trajectory, then Hubble should clearly see them as separate objects. But the November 11th images from the Nordic Optical Telescope show only a single, condensed point of light surrounded by a normal-looking coma. No multiple condensations, no secondaries, no visible fragments of any kind. This leaves only three possibilities. The comet did not fragment, even though the mass loss calculations suggest it should have. The fragments are still so close together that they appear as one object, which is unlikely 2 weeks after perihelion. Or the comet never lost that much mass in the first place, meaning the true mass loss was far smaller than 5 to 50 billion tons. Here is another prediction we can test. If 3I Atlas did fragment near perihelion, the individual pieces would not stay together. Even tiny differences in their orbits, called differential velocity, would cause them to drift apart. Tidal forces from the Sun would also pull on each fragment slightly differently, depending on how far each one is from the Sunday. Avi Loeb calculated that, if fragmentation occurred, the pieces should be separating at speeds of roughly 10 to 100 meters per second over the 2 weeks between the perihelion on October 29th and the observations on November 11th. That would create the following separations. At the low end, 10 meters per second multiplied by 1.2 million seconds gives about 12,000 kilometers. At the high end, 100 meters per second multiplied by 1.2 million seconds gives about 120,000 kilometers. Separations of 12,000 to 120,000 kilometers would be obvious. They would appear in the November 11th images as multiple bright condensations clearly distinct from one another, but no such fragments are visible. This leaves three options. No fragmentation occurred. Fragmentation did occur, but it was far less severe than the mass loss calculations imply. Or, for some reason, the fragments are remaining clustered together despite the natural forces that should be pulling them apart. There is one more historical example that shows just how dramatic comet fragmentation can be. Comet Shoemaker-Levy 9, which collided with Jupiter in July 1994. Shoemaker-Levy 9 was torn apart by Jupiter's tidal forces during a close approach in July 1992. The nucleus split into at least 21 separate fragments, each of which went on to strike Jupiter 2 years later. What did that fragmented comet look like during the 2 years between its breakup and its impact with Jupiter? Hubble captured extraordinary images showing 21 distinct fragments, labelled from A through W, each fragment surrounded by its own small coma, all of them stretched along the orbit like pearls on a string, a total length of more than 1 million kilometers. Individual fragment sizes ranging from half a kilometer up to 2 kilometers in diameter. The breakup was so unmistakable that even amateur astronomers using 8 to 10-inch telescopes could see multiple nuclei. Now, Shoemaker-Levy 9 shattered because of Jupiter's tidal forces, not because of thermal stress from the Sunday. But the principle is the same. When a comet nucleus breaks apart, the pieces spread out and become individually visible. So if 3I Atlas really split into 16 or more fragments at perihelion, then 2 weeks later we should see multiple bright points embedded in the coma. But we do not. Let me be very clear about the comparison. If 3I Atlas lost around 5 billion tons through normal fragmentation and sublimation, we should expect to see the following. Between 10 and 20 visible fragments, or a single nucleus surrounded by a coma, 1 to 2 million kilometers in diameter, gas production rates of 10,000 to 50,000 kilograms per second of carbon dioxide, measurable in spectroscopy, a dust tail between 2 and 5 million kilometers long, a brightness between magnitude 8 and 10, making it visible in small amateur dyes, telescopes, and obvious changes when you compare images taken before and after perihelion. If 3I Atlas lost around 50 billion tons, the expectations are even more extreme, between 50 and 100 or more visible fragments, or complete disintegration into a diffuse cloud, spectroscopic gas production above 100,000 kilograms per second of carbon dioxide, debris spread across 5 to 10 million kilometers, a brightness between magnitude 6% of and 8, visible in binoculars or even to the naked eye, and a dramatic, unmistakable transformation of the comet's appearance. Now compare that to what the images from November 11th actually show. A single, intact nucleus. No visible fragments at all. A coma roughly 100,000 to 200,000 kilometers in diameter, modest by comet standards. Post-perihelion gas production has not yet been fully measured, but early indications suggest only on the order of a few thousand kilograms per second. A developing dust tail only a few 100,000 kilometers long. A brightness between magnitude 11 and 12, requiring an 8 to 12-inch telescope to observe. And when you compare pre-perihelion and post-perihelion images, the comet looks broadly similar, with only a moderate increase in activity. In other words, the comet looks like it went through a normal perihelion passage with a modest boost in outgassing. It does not look like an object that just lost between 15 and 50% of its entire mass. And that is the core of the mystery. This is not speculation. This is not a matter of interpretation. It is a direct comparison between three things. What the mathematics says must have happened, what historical precedent says we should see if that happened, and what we actually observe in the sky. The three do not match. Something is wrong. Either our observations are somehow missing something enormous and obvious, which seems unlikely, considering how many telescopes are watching, or our mass loss calculations are wrong, which also seems unlikely, because they are built on straightforward conservation of momentum, or something about 3I Atlas is fundamentally different from every other comet we have ever studied. To understand what should have happened to 3I Atlas at perihelion, we need to walk through the physics of what happens when a frozen object from deep space encounters the sun's radiation for the first time in billions of years. This is not speculation. This is thermodynamics. This is radiation physics. This is chemistry we have tested on thousands of comets across centuries of observations. 3I Atlas almost certainly formed in another star system. Its trajectory suggests it comes from the galactic thick disk, an old stellar population which puts its origin roughly 8 to 10 billion years in the past. After being ejected from its home system, it drifted through interstellar space for billions of years. Out there, far from any star, the temperature settles to the same value everywhere, the temperature of the cosmic microwave background, the faint afterglow of the Big Bang. That temperature is about 2.7 Kelvin or roughly 270 degrees Celsius below zero. For billions of years, 3I Atlas was frozen at a temperature just barely above absolute zero. At such extreme cold, molecular motion almost completely stops. Ice becomes perfectly crystalline and rigid. Chemical reactions cease. Sublimation does not occur. The comet is inert, unchanged, and locked in deep freeze. Then, sometime in the recent cosmic past, maybe within the last few million years, 3I Atlas entered the outer reaches of our solar system. Its velocity, roughly 26 kilometers per second relative to the Sun, carried it gradually inward, and for the first time in eons, this frozen, interstellar relic began to feel the warmth of sunlight. Let's track how the temperature of 3I Atlas increased as it moved inward toward the Sunday. At 5 astronomical units, where it was discovered in early July 2025, the sunlight hitting it was about 55 watts per square meter. Its surface temperature stabilized around 125 to 150 Kelvin. That means the comet warmed by roughly 120 to 145 degrees compared to deep space temperature. This warming was enough to start sublimating the most volatile ices, such as carbon monoxide and molecular nitrogen. At 3 astronomical units in August 2025, solar energy increased to about 150 watts per square meter. Surface temperature rose to around 165 to 185 Kelvin. Carbon dioxide ice began to sublimate more actively as patches reached the 195 Kelvin threshold. At 2 astronomical units in September 2025, sunlight reached roughly 340 watts per square meter. The surface temperature climbed to about 210 to 225 Kelvin. Carbon dioxide sublimation became vigorous. The warmest on, regions of the comet were approaching the point where water ice itself begins to sublimate. At 1.36 astronomical units, its perihelion on October 29, 2025, solar energy peaked at about 735 watts per square meter. The sunlit side reached roughly 245 to 265 Kelvin. Carbon dioxide sublimation became extremely tail. Intense water ice was actively sublimating. The total temperature increase from deep space background was about 240 to 260 degrees. To put that into perspective, the comet warmed from about 2.7 Kelvin almost, absolute zero to roughly 260 Kelvin. That is a temperature jump of nearly a factor of 100. It is like taking something frozen in Antarctica at almost minus 270 Celsius and placing it somewhere around minus 10 to 0 degrees Celsius, an environment where ice melts and evaporates rapidly. But the story is not that simple. The heat from the sun does not instantly penetrate the entire comet. It only warms the outer layers at first. Thermal energy has to work its way inward through the mixture of ice and dust by slow thermal conduction. The thermal diffusion equation tells us how fast heat can actually move into a comet. In simple terms, it tells us how deep the warming reaches. The formula for skin depth, the depth to which heat penetrates, is skin depth equals the square root of thermal conductivity times time divided by density times specific heat. Now let's plug in comet numbers. Thermal conductivity of porous ice is extremely low, roughly 0.001 to 0.01 watts per meter Kelvin. Density is about 500 kilograms per cubic meter, and the specific heat capacity of ice is around 2,000 joules per kilogram Kelvin. The comet spent about 4 months traveling from 5 astronomical units to perihelion. That is roughly 10 million seconds. Using those numbers, the skin depth comes out to about 0.3 meters, only 30 centimeters. So in 4 months, heat from the sun penetrates less than half a meter into the surface. This creates a very steep temperature gradient. The sunlit surface reaches around 260 Kelvin. 10 centimeters deep, the temperature is about 220 Kelvin. 30 centimeters deep, around 180 Kelvin. 1 meter deep, close to 100 Kelvin, almost unchanged. And the core remains essentially frozen at interstellar temperatures, around 3 to 10 Kelvin. The comet becomes a two-layered temperature structure, a thin, warm shell wrapped around a frozen interior, and that has huge consequences. First, only the surface ice is warm enough to sublimate. The vast majority of the comet stays frozen solid. Second, enormous thermal stresses build up. The surface warms and expands, while the interior remains rigid and ice cold. This creates mechanical strain throughout the structure. Third, and most important for the mass loss problem, outgassing is limited by how much ice the sun can actually heat. And because heat only reaches 30 centimeters deep, mass loss can only come from that thin outer layer. This limitation is absolutely critical for the entire mass loss calculation that follows. If only a 30 centimeter surface layer is warm enough to sublimate intensely, then all the mass loss must come from that thin outer shell. Let's apply that to a sphere about 5.6 kilometers across the size measured by Hubble. The total surface area is roughly 98 square kilometers. The active sublimation depth is just 0.3 meters, so the volume of material warm enough to sublimate is 98 square kilometers times 0.0003 kilometers, which equals about 0.03 cubic kilometers. Multiply that by the density, 5 times 10 to the 11 kilograms per cubic kilometer, and you get roughly 1.5 times 10 to the 10 kilograms. That is about 15 billion tons of material, so the entire warm layer contains only enough mass to supply the 5 to 15 billion tons suggested by the jet calculations, but only if the entire active layer evaporates completely. For that to happen, several extreme things must be true. The entire 30 centimeter skin must be stripped off. Fresh ice underneath must immediately begin sublimating, and the process would continue again and again as the thermal wave slowly works deeper into the comet. Idea is possible. It is known as catastrophic sublimation, and it has been invoked for comets that suddenly brighten or erupt. But if catastrophic sublimation actually happened here, we should clearly see dramatic changes to the surface between before and after perihelion, a noticeably smaller nucleus because the entire outer layer would have been eroded away, and a large quantity of debris that is impossible to hide. Now let's calculate what the comet could actually do with the energy it received from the Sun at perihelion. Solar input. The surface area of a 5.6 kilometer comet is about 98 square kilometers. At a distance of 1.36 astronomical units, the Sun delivers roughly 735 watts per square meter. If we assume total absorption of sunlight, which is physically impossible but gives an upper limit, the comet absorbs 735 watts per square meter multiplied by 98 million square meters, which equals about 7.2 times 10 to the 10 watts. That is 72 gigawatts. In other words, about 50 large nuclear power plants worth of energy. Energy required for the claimed sublimation. Carbon dioxide ice needs about 600 joules to sublimate each gram, to lose 5 billion tons in 30 days. The comet must shed 1.9 million kilograms every second, and the power needed to sublimate that much carbon dioxide ice is 1.9 million kilograms per second, multiplied by 600,000 joules per kilogram, which equals 1.1 times 10 to the 12 watts. That is 1,100 gigawatts of power. Compare that to what the Sun actually provides at perihelion, 72 gigawatts. The required power is 15 times larger than the power available. And that gap remains, even if we assume completely unrealistic conditions. Perfect absorption, meaning the comet is pitch black, no heat loss to know, and every bit of absorbed energy going into sublimation alone. Even under those impossible assumptions, the comet still falls short by a factor of 15. The physics simply does not add up. For a mass loss of 50 billion tons, the energy deficit becomes even more extreme, a shortfall by a factor of 150. In simple terms, the Sun cannot deliver enough energy in the available time and with the available surface area to sublimate that much ice. But the energy problem is actually worse than that. Up to now, we assumed 100% absorption, meaning every bit of sunlight that hits the comet gets absorbed. That is physically impossible. Comet surfaces are dark, but they are not perfectly black. Typical comet reflectivity is about 0.04. That means 4% of sunlight is reflected and 96% is absorbed. However, when sublimation removes the dark crust and exposes fresh ice, the reflectivity increases dramatically. Fresh water ice reflects 50 to 70% of incoming light. Fresh carbon dioxide ice behaves similarly. So if 3I Atlas exposed fresh ice during perihelion, and the November color change from reddish to bluish suggests exactly that, then the surface became far more reflective. More reflection means less absorbed energy. Less absorbed energy means even less power available for sublimation. This creates a negative feedback loop. 1. Sublimation removes the dark crust and exposes clean, bright ice 2. Bright ice reflects much more sunlight 3. The surface absorbs less energy 4. Sublimation slows down 5, which makes it even harder, nearly impossible, to erase billions of tons of material. And there is another complication. All our earlier calculations quietly assumed that the comet is lit by the Sun continuously. That is not true. Comets rotate. We do not yet know the exact rotation period of 3I Atlas, but brightness variations suggest something in the 10 to 40 hour range. Let's use 20 hours as a reasonable estimate. That means only half the surface is illuminated at any moment. The other half is in darkness. The dark side cools rapidly by radiating heat into space, and sublimation on the night side essentially shuts down, so the power available for cast. Sublimation is only from the lit half of the comet. That reduces the usable solar power from about 72 gigawatts down to about 36 gigawatts. And each section of the surface only receives that sunlight for roughly 10 hours out of every 20-hour rotation. Put all of this together, and the energy shortfall becomes even more severe. The Sun simply cannot supply the power needed to remove billions of tons of ice in a single month. The bright angel, the October 28 and 29 brightening, during perihelion, when 3I Atlas passed behind the Sun from Earth's point of view, only space-based observatories could see. It, SOHO, Stereo A, and the GOES 19 satellite all captured the event. Astronomers Qicheng Zhang and Carl Battams analyzed the data and saw something remarkable. 3I Atlas brightened sharply and unexpectedly, reaching magnitude 7 to 8 at perihelion. For comparison, at discovery on July 1st, magnitude 17.5, late August, magnitude 13 to 14, late September, magnitude 11 to 12, perihelion, October 28 and 29, magnitude 7 to 8, early November, back down to magnitude 11 to 12, the comet became about 2 magnitudes brighter than standard models predicted. And remember, the magnitude scale is logarithmic. A difference of 2 magnitudes means the comet became about 6 times brighter than expected. Why would a comet suddenly brighten like that? Possibility 1. Increased surface area from fragmentation. When a nucleus breaks apart, the total surface area increases dramatically. More surface area means more sublimation, which means more brightness. If the nucleus split into 16 equal pieces, each piece would have 1/16 the volume. Each piece would have about 1/6 the original surface area. Together, all 16 pieces would have roughly 2.5 times the original total surface area. A 2.5 times increase in surface area gives only about 1 magnitude of brightening. To reach the observed brightening about 6 times, you would need around 40 pieces, not 16. Possibility 2. An outburst. Comets sometimes undergo sudden outbursts when volatile ice pockets rupture, a landslide exposes fresh material, or a phase change occurs deep in the ice. Outbursts can brighten a comet by factors of 10 to 100, but they usually last hours, or at most a day. The brightening of 3I Atlas lasted several days around perihelion, far longer than a typical outburst. Possibility 3. Catastrophic sublimation. Perhaps the entire active surface layer sublimated rapidly in a short period, dumping an enormous amount of gas and dust into space. But then we return to the central problem. Where did the energy come from to drive such a rapid release? The sun simply cannot provide enough power for that scenario. There is something else. During perihelion, space-based instruments reported that 3I Atlas appeared distinctly blue, bluer than the sun itself. That is not normal. Typical comet behavior produces the opposite. Dust scatters sunlight and usually makes the comet appear slightly redder. Organic material on the surface adds a reddish tint. Fresh ices often scatter evenly or slightly redwood. In other words, a comet should look a little red, but 3I Atlas looked blue. That is unusual, and it very likely means the surface or the coma changed in a way we don't normally see, perhaps through fresh ice exposure, unusual particle sizes, or something else entirely. Possible explanations for the blue color. First explanation: ionized gas emission, specifically ionized carbon monoxide. When carbon dioxide molecules are struck by ultraviolet light from the sun, they break apart. The carbon monoxide that remains can then be ionized. Ionized carbon monoxide, called CO+, emits a strong blue-violet glow, especially around 420 nanometers. If 3I Atlas was releasing enormous amounts of carbon dioxide near perihelion, and if much of that carbon monoxide became ionized by the intense ultraviolet radiation, the blue glow from CO+ could dominate the comet's appearance. It could easily overwhelm the reddish tint that usually comes from dust scattering sunlight. This requires 3 things: very high carbon dioxide production, which fits perfectly with the Webb telescope's finding that 3I Atlas is 87% carbon dioxide, strong ultraviolet radiation, which is definitely present at 1.36 astronomical units, and a low dust-to-gas ratio, so the blue emission is not drowned out by red dust scattering. This is the mainstream scientific explanation, and it is probably correct. Second explanation: exposure of fresh ice. If the comet's dark reddish surface was completely sublimated away, exposing fresh ice underneath, the newly exposed surface could appear slightly blue. Fresh ice sometimes looks blue, like Earth's glaciers, because the red wavelengths get absorbed more efficiently. But this alone cannot fully explain the color, because fresh ice is mostly white. You would need almost no dust at all to avoid the usual red hue, and the blue tint would fade quickly as the surface becomes weathered by space. So this explanation feels incomplete. Third explanation: something else. Physicist Avi Loeb posed a provocative question. Does it employ a power source hotter than the Sun? He is not claiming that is true. He is pointing out that a comet appearing bluer than the Sun implies, in strict thermodynamic terms, a temperature higher than the Sun's own surface, which is impossible through ordinary solar heating. Most scientists think this line of questioning is unnecessary because the ionized carbon monoxide explanation fits the data. But Loeb's point is simple. Anomalies sometimes highlight gaps in our understanding. And here is the key test. If December spectroscopy detects strong CO+ emission lines in the blue region, the case is closed. If it does not, then something is missing from our explanation. Now, something even stranger. On October 30th, 2025, just one day after perihelion, NASA's Jet Propulsion Laboratory reported non-gravitational acceleration in the orbit of 3I Atlas. Non-gravitational acceleration means one thing. The comet is not moving only under the pull of gravity. Something else is pushing it. For most comets, a slight push on their orbit is normal. It is simply the rocket effect. Gas blasting out of the nucleus acts like a tiny thruster, nudging the comet off its purely gravitational path. But the amount of acceleration tells us something important. It tells us how much mass the comet is ejecting. NASA's measurements showed two components of acceleration. Away from the Sun, about 135 kilometers per day squared, that is 0.0181 meters per second squared, sideways, perpendicular to the orbit, about 60 kilometers per day squared, that is 0.008 meters per second squared. These numbers sound tiny, but over the span of several weeks, they produce clear, measurable deviations in the comet's trajectory. So, how much mass does it take to create that kind of push? The logic is straightforward. The force from outgassing depends on the mass being expelled each second, multiplied by the speed at which that gas leaves the comet. Meanwhile, the acceleration of the comet depends on the total mass of the nucleus multiplied by the measured acceleration. If you combine these ideas, you get the mass loss rate, the amount of material the comet must be ejecting every second. Using the numbers, comet mass, about 33 billion tons. Radial acceleration, 0.0181 meters per second squared. Outflow speed, roughly 500 meters per second, which is normal for carbon dioxide gas. When you put those values together, the result is a mass loss rate of about 1.2 million kilograms per second. That is more than 1 million kilograms every single second. Now let's scale that over the 30 days around perihelion. That comes to roughly 3 times 10 to the 12 kilograms, or about 3 billion tons. This matches the earlier jet-based estimate extremely well. Both methods point to the same ballpark value, several billion tons of mass lost. And that raises a critical question. Has any comet in history ever lost 10% of its total mass in just 1 month, without fragmenting, without brightening dramatically, and without leaving behind unmistakable debris? No, not a single one. When we look back at historical comet behavior, a very clear pattern emerges. Comet Linear, in the year 2000, lost roughly 20 to 30% of its total mass. It shattered into more than 60 separate pieces. Comet Schwarzmann-Wachmann 3, over multiple returns, lost about 30% of its mass. It also fragmented into more than 60 pieces. Comet Ison, in 2013, lost essentially 100% of its mass. It completely disintegrated. The pattern is simple and consistent. Whenever a comet loses more than 10% of its mass in a short period of time, it breaks apart, every time. 3I Atlas supposedly lost between 10 and 15% of its mass. By that logic, it should have fragmented, but the images from November 11th show something very different. A single nucleus, clearly intact, with no visible fragments. And this brings us to one more striking detail from the perihelion observations. The anti-tail, the jet that appears to point toward the Sun, never went away. Normally, an anti-tail is just a perspective trick. When Earth crosses the comet's orbital plane, the dust tail, which always points away from the Sun, can look like it has a sunward component. This illusion only lasts a few days as our viewing angle changes. But with 3I Atlas, the anti-tail was observed again and again. July 21st, in a Hubble image, November 9th, still visible in wide-field observations, November 11th, still present in the Nordic optical telescope images. That is more than 3 months of a persistent sunward structure. A geometric illusion cannot last that long. The viewing geometry simply does not stay that constant. If the antitail is real, if material is actually flowing toward the sun, then something powerful must be driving. To push gas and dust against the solar wind, the comet would need extremely high gas production, continuous outgassing lasting for months, and enormous mass loss. Exactly the numbers we calculated earlier. So the long-lived antitail strengthens the case for sustained, powerful outgassing. And yet, there is still no debris, no fragments, no massive coma, no brightening that matches the expected mass loss. The more evidence we gather, the stranger the picture becomes. Let's summarize what the physics says should have happened to 3I Atlas. First, the temperature. The sunlit surface warmed from about 3 Kelvin to around 260 Kelvin. Second, thermal stress. That kind of uneven heating creates enormous internal strain as the warmed outer layers expand while the deep interior stays almost frozen. Third, the available energy. Once you account for rotation and the fact that the surface does not absorb all the sunlight that hits it, the comet only has on the order of 36 gigawatts of usable solar power. Fourth, the energy required. To sublimate 5 billion tons of carbon dioxide ice in about a month would take roughly 1,100 gigawatts. Fifth, the gap. That is an energy shortfall by a factor of about 30. Sixth, the expected outcome. With that kind of shortfall, physics says we should see either modest mass loss less than about 500 million tons, or significant fragmentation to increase the surface area, or some other energy source at work. Seventh, brightness. The comet brightened by about 2 magnitudes more than standard models predicted. Eighth, colour. It became distinctly blue, which strongly suggests ionized carbon monoxide emission from massive carbon dioxide breakdown. Ninth, non-gravitational acceleration. NASA's trajectory measurements imply that 3 to 5 billion tons of material were lost. 10th, the persistent antitail. A sunward jet remained visible for more than 3 months, pointing to sustained, powerful outgassing over an extended period. Put together, the observations, the brightening, the blue colour, the measured acceleration, and the long-lived antitail all point toward massive mass loss on the order of billions of tons. But the energy budget says that much mass loss is impossible using solar heating alone, unless the comet broke apart and dramatically increased its surface area. And yet, the post-perihelion images show no sign of fragmentation. Something does not add up. We are left with a small set of possibilities. The comet did fragment, but the fragments are somehow invisible to us, which seems unlikely. The mass loss was much smaller than we calculate, but then what produced the strong non-gravitational acceleration? The energy came from a source other than sunlight, but what source could that be? Or our understanding of comet sublimation is incomplete, which is possible, but then we have to ask, what exactly are we missing? The observations coming in December will test every part of this directly. We've now framed the problem clearly. The next step is to examine, one by one, every serious hypothesis for where 50 billion tons of cometary material could be hiding, or why the numbers might be misleading us. I'm going to steelman each explanation. That means giving the strongest, most generous possible version of every hypothesis, even the ones that seem unlikely. Then we'll compare each of them with the actual evidence. One of the first ideas people raise is simple. Maybe all that material really did escape, but it escaped as gas, and gas is mostly invisible. Carbon dioxide is transparent. You breathe it out all the time, and unless water vapor condenses in cold air, you never see anything. The Webb telescope already told us that about 87% of this comet's volatile output is CO2, not water vapor. So most of what left nucleus would be invisible to the eye. And we know comets often produce far more gas than dust. Their dust-to-gas ratios can vary wildly, from just a few percent all the way up to parity. If 3I Atlas happens to sit at the very low dust end of that range, maybe the bulk of its outgassing didn't carry much solid material with it. If that's true, we would only see a modest amount of dust, even if the total gas loss was enormous. There are reasons this idea sounds appealing. Our spectroscopy in September was limited. Ground-based observatories can't easily see the infrared bands of CO2, and the comet was low in the sky from many locations. If most of the mass escaped as transparent carbon dioxide, and if dust production was unusually low, then maybe the gas simply slipped past our eyes and our cameras. But the problems come quickly. Historically, even gas-rich comets that lose far less mass than this still produce unmistakable visible signatures. Comet Hale-Bopp had a dust-to-gas ratio of about 0.3, and yet it formed a tail over 100 million kilometers long. Comet Hyakutake was even more gas-dominated, roughly 0.1, and still had a huge, obvious tail. If 3I Atlas really expelled billions of tons, then even with an extremely low dust ratio, say 1%, we would still expect tens of millions to hundreds of millions of tons of dust. That is comparable to what Comet Linear released when it fragmented, and Linear was easily visible to the naked eye. And gas isn't truly invisible in practice. Even transparent gases scatter sunlight. They fluoresce, they ionize. Ionized carbon monoxide CO+ produces strong blue emission lines, and we have already seen hints of that. If the mass loss really was in the multi-billion ton range, the coma should be enormous, millions of kilometers across, simply from sunlight interacting with the expanding gas. Instead, we see a coma only about 100,000 to 200,000 kilometers across, far smaller than what massive gas release would produce. Then there's the spectroscopy. Gas may be invisible to the eye, yes, but not to instruments. CO2 has very strong infrared signatures, and the James Webb Space Telescope is designed precisely to detect them. If 3I Atlas had dumped 5 to 50 billion tons of CO2 into space, the emission lines would be intense, bright, and unmistakable. They would dominate the entire spectrum. December's spectroscopic observations will confirm this one way or the other, but based on what we have already seen, there is no sign of the overwhelming line intensity that such a mass loss would produce. All of that pushes the transparent gas explanation into an uncomfortable corner. It might contribute maybe the comet really is unusually gas-rich. Maybe it produces very little dust, but that alone cannot hide billions of tons. At best, it explains part of the discrepancy, not the whole mystery. Another idea people raise is that maybe the comet is simply larger than we think. If the nucleus were not the roughly 5.5 kilometers Hubble measured, but instead something 10, 15, or even 20 kilometers across, the situation would look very different. A larger object has much more surface area, 4 to 16 times more, depending on the size. More surface area means more solar energy absorbed, and if the comet is that much larger, then those 5 to 50 billion tons represent a smaller fraction of its total mass. In that scenario, the energy budget softens, the percentage of mass lost shrinks, and the entire problem feels less extreme. It is not a crazy suggestion. Size estimates always depend on albedo, on how reflective the surface is. We do not measure size directly. We measure brightness and infer size based on assumptions about reflectivity. If the surface is darker than we think, the same brightness corresponds to a larger object, and the Hubble images show a bright central region enveloped by coma. You could argue that what we interpret as the solid nucleus might actually include unresolved inner vapor, making the true nucleus larger. Even Loeb pointed out that if the object were much larger, the statistical oddity 3I Atlas being massively larger than Oumuamua would look a little less bizarre. But the problems with this idea come quickly. Hubble's estimate is not a loose guess. The July 21st image clearly resolved the structure of the inner coma and constrained the nucleus to under about 6 kilometers. To inflate that to 20 kilometers, you would need an albedo of roughly 0.003, darker than charcoal, darker than any comet nucleus ever measured. And making the comet that large triggers a cascade of contradictions. A 20-kilometer body would weigh trillions of tons, not tens of billions. If that were true, the modest pre-perihelion outgassing should have produced virtually no measurable non-gravitational acceleration, and yet we did see early hints of it, and after perihelion, the acceleration became strong. Those accelerations only make sense if the comet's mass is in the tens of billions of tons range, not the trillions. The dynamics simply do not fit a giant nucleus. And even if we set all of that aside, being larger doesn't fix the underlying physical bottleneck. Heat only penetrates into the outer tens of centimeters during the entire inbound leg. The thermal skin depth does not care whether the comet is 5 kilometers wide or 50. The layer that actually warms enough to sublimate is still just that thin outer shell. The amount of ice available for rapid sublimation barely changes. The energy shortfall remains exactly the same. December's Hubble observations will settle this conclusively. If the nucleus is smaller after perihelion, then the 6-kilometer estimate was essentially correct. And if it hasn't changed size at all, that also confirms the original number, because a 20-kilometer nucleus would not lose a few billion tons of material without visibly shrinking. So the maybe it's much bigger than we think idea simply doesn't rescue the scenario. At best, the true size might be off by a factor of 2, but even that doesn't resolve the energy deficit or the mass loss contradictions. The pieces just do not lock together. Another possibility people bring up is that maybe the outflow velocity was higher than assumed. If the gas wasn't moving at roughly 400 meters per second, but instead at a kilometer per second or more, the whole picture would shift. Faster gas reaches the observed distances in less time. Less time flowing means less total mass needed to form the same long, extended jets. In that version of events, the jets could look identical to what we see while representing far smaller mass loss. There are reasons why this idea gets attention. Some supervolatile ices, like carbon monoxide, can sublimate at lower temperatures and send molecules out faster. Lighter molecules always move faster at a given temperature. And on some comets, narrow collimated jets do shoot out at velocities higher than the typical thermal speed. Water outgassing can approach a kilometer per second, and even though 3I Atlas only has about 4% water by mass, it's possible for a small amount of fast water vapor to dominate specific jet-like features. So, at first glance, there are plausible mechanisms that could push the gas toward the high end of the velocity range. But the idea runs into hard physical limits almost immediately. Outflow velocity is not something you can freely adjust. It is tied directly to temperature, roughly proportional to the square root of it. To double the velocity, the gas needs roughly 4 times the temperature. At 1.36 astronomical units, the surface temperature is fixed by the sunlight available. It cannot rise far enough to produce ultra-fast outflows unless some other energy source is involved. And the Webb data already showed the composition is overwhelmingly dominated by CO2, about 87% by mass. At perihelion temperatures, CO2 produces velocities around 400 to 500 meters per second. It simply does not reach a kilometer per second unless the material is much hotter or unless something is mechanically accelerating the flow, and there's no evidence for that. There is an even bigger problem. Increasing the velocity actually makes several existing issues worse. Higher velocity means much higher ram pressure, because the force exerted on the solar wind scales with velocity squared. Jumping from 0.4 kilometers per second to 1 kilometer per second multiplies the required gas density by more than 6. That means even more mass would be required to produce the sunward jet, not less. And the antitail itself already constrains the velocity. The antitail extends only about 1 million kilometers before being turned by the solar wind. That turnover distance is extremely sensitive to velocity. If the gas were moving significantly faster, the antitail would reach much farther. But what we actually observe lines up perfectly with a flow speed of around 0.4 to 0.5 kilometers per second. So while faster gas sounds like a convenient escape hatch, it collapses as soon as you run the numbers. The physical temperature simply isn't high enough to produce velocities that would meaningfully reduce the required mass, and pushing the speed higher only creates new contradictions with the observed antitail and with the ram pressure needed to hold that sunward jet in place. It just doesn't resolve the discrepancy. Another idea people bring up is that the jets might be far more tightly collimated than they look narrow beams, rather than broad, diffuse fans. If the actual cross-section of the flow were much smaller, you could keep the same density and the same velocity, yet slash the total amount of material needed. In that scenario, the jets would still look dramatic in photographs, but the true mass loss could be tiny compared to what we've been assuming. And this isn't unreasonable at first glance. Spacecraft have shown us that comets can indeed produce sharply focused jets. Tempel 1 had discrete vents. Rosetta captured astonishingly narrow jets blasting from tiny patches on Comet 67P, some only tens or hundreds of meters across, and long exposures blur things. Scattered light widens everything. A thin, needle-like jet can easily smear into something that looks like a wide cone. So you could imagine a structure that appears 100,000 kilometers across, actually originating from a vent only a few dozen meters wide. If that were truly the case, if the effective cross-section were 100 times smaller than it looks, then the required mass flux would also drop by a factor of 100. That would make the entire mass loss problem dramatically easier to swallow. But the actual images don't support that interpretation. The November 9th observations show broad, diffuse structures, not sharp, needle-like beams. These are not narrow laser-style jets. They are wide, fan-shaped outflows, and their visible width is in the hundreds of thousands of kilometers. And even if a jet starts out tightly collimated near the surface, it can't stay narrow over interplanetary distances. Geometry guarantees divergence. A 10-meter wide vent becomes a 100-kilometer wide plume, and then a 100,000-kilometer wide structure, once it travels out to 1,000,000 kilometers from the nucleus, even with very mild spreading. And then there's the solar wind issue. To hold its shape against the solar wind long enough to create a persistent sunward anti-tail, the gas, 1,000,000 kilometers from the nucleus, must have a certain minimum density. That density, multiplied by the observed physical area of the structure, gives you the total mass flow. You can't shrink the area arbitrarily while still producing the observed push against the solar wind. If you make the area smaller, the density must rise proportionally, which means more mass, not less. So narrow jets might trim the numbers slightly, maybe by a factor of 2 or 5, but they can't give us the order of magnitude reduction needed to reconcile everything we see. Collimation helps, but nowhere near enough to close the gap. Another possibility is that maybe 3I Atlas is simply far more massive than we think. If the comet isn't 33 billion tons, but something like 300 billion tons or even a few trillion, then losing 50 billion tons wouldn't be catastrophic. In that scenario, the comet might only shed 5 to 15% of its mass, instead of something close to its entire bulk, which would make survival as a single nucleus much more plausible. It wouldn't fix the energy problem, but at least the percentage loss would feel more reasonable. And there are reasons someone might think the mass could be underestimated. The 33 billion ton figure isn't a direct measurement. It comes from not detecting any non-gravitational acceleration before perihelion, combined with the gas production rate that Webb measured in August. Both of those numbers carry uncertainties. If the pre-perihelion outgassing was stronger than Webb could see, or if the activity was uneven in a way that masked acceleration, then the comet could be significantly heavier. After all, we don't have any direct way of weighing it, no gravitational tugs on nearby planets, no spacecraft flyby. Everything is inferred. A larger mass would also soften one of the statistical headaches. A trillion-ton interstellar comet is far more plausible than one that's only 33 billion tons. It reduces the feeling that we just happened to get improbably lucky. But this idea immediately collides with other observations. If the comet were hundreds of billions of tons, then the mild outgassing Webb saw in August, about 150 kilograms per second, should still have produced some measurable non-gravitational acceleration. Yet there was none. Zero. The absence of early acceleration is what forced the mass estimate upward in the first place. Ironically, trying to push the mass even further upward contradicts the very data that required it. There's also the size constraint. Even using a typical comet density of 500 kilograms per cubic meter, a mass of 300 billion tons would require a nucleus around 10 to 11 kilometers across. But Hubble's imaging limits the size to under 5.6 kilometers. The only way to fit that much mass into such a small object would be if the density were more like solid rock above 2,000 kilograms per cubic meter, which would make it not a comet at all. And that contradicts everything we know from the composition. Extremely volatile, 87% carbon dioxide ice, only 4% water ice, and a porous structure. A solid rock wouldn't behave this way. And even if we ignore all of that, it still doesn't fix the biggest contradiction. A heavier comet doesn't magically provide the enormous amount of energy needed to sublimate 50 billion tons of carbon dioxide ice. It just changes the fraction of the mass that would have been lost. The energy shortfall remains exactly the same. So while increasing the mass sounds like it should relieve the pressure, it ends up breaking more things than it fixes. You can't have a comet that is simultaneously heavy enough to hide 50 billion tons of missing material and yet light enough not to show early acceleration. The numbers simply refuse to fit together. Another idea is that maybe the debris really is there, but it has dispersed and faded so much that we can't see it anymore. Gas expands rapidly. At an outflow speed of about 0.4 kilometers per second, material released at perihelion would travel nearly 500,000 kilometers in just 2 weeks. Spread that gas over a huge volume and its density drops dramatically. Dust behaves the same way. The smallest grains get pushed outward by solar radiation pressure, spreading out and fading quickly. After a couple of weeks, perhaps the entire cloud is so diffuse that even the major observatories can't detect it. And depending on the viewing geometry, whether we see the debris edge on or face on, its visibility could change a lot. It's a reasonable thought, but it runs into multiple problems. The first problem is that we have very clear historical expectations for how long comet debris remains visible, and the answer is far longer than 2 weeks. Comet Linear's debris stayed obvious for more than 6 months after it broke apart. The fragments of Schwarzmann-Wachmann 3 were visible for years. Even ordinary dust tails remain easy to detect for months. If 3I Atlas truly expelled 5 to 50 billion tons of material, that debris cloud should still be present and obvious through mid-November. 2 weeks is nowhere near enough time for that much material to disperse into invisibility. The second problem is instrumental sensitivity. Hubble and the James Webb Space Telescope routinely detect extremely faint, diffuse structures, thin nebulae, low surface brightness galaxies, expanding shells of gas from dying stars. A dispersed coma of comet debris is trivial by comparison. If that material existed in any significant amount, these telescopes would see it. Then there is the behavior of the gas itself. CO2 molecules do not disappear quickly. They do not break apart immediately in sunlight. They persist for weeks or even months, and spectroscopy should still reveal their presence. Long after the peak of sublimation, a gas release of billions of tons would leave a spectroscopic fingerprint that would not just vanish in a matter of days. And, perhaps most telling, the images from November 11th do not show an expanding cloud. They show a modest, fairly stable coma, roughly 100,000 to 200,000 kilometers across. If billions of tons of material had been expelled just 2 weeks earlier, we should see a dramatically larger, more diffuse cloud. Instead, the coma looks normal, undisturbed, like a comet experiencing routine outgassing, not catastrophic mass loss. So while the "it dispersed and faded" explanation fits intuitively with how gas behaves in space, it does not hold up against what we know from past comets or what our instruments can detect. It does not explain why so much material orders of magnitude more than what destroyed comets like Linear and Ison has somehow left no trace at all. Another possibility is that non-gravitational acceleration was simply misinterpreted. Maybe the trajectory deviation measured after perihelion does not really require billions of tons of mass loss. Perhaps the astrometric data has larger uncertainties than assumed, or the acceleration is real but caused by something other than outgassing. After all, measuring tiny positional shifts across millions of kilometers is difficult. Very small errors in timing, calibration, or in locating the comet's center can propagate into the orbital solution and distort the inferred acceleration. And comets do experience small extra forces, solar radiation pressure, or thermal re-emission effects like the Yarkovsky effect, so maybe what JPL detected was something like that rather than a rocket-like push from sublimation. But this idea quickly runs into problems. JPL is extremely good at this. They have modelled non-gravitational forces for hundreds of comets, and they know exactly what the signatures look like, what the uncertainties are, and how to separate real forces from observational noise. Their reported uncertainty bars already include every known source of error, and in this case, it is not just JPL. Several independent orbit determination groups reached the same conclusion. The acceleration they found is statistically significant, persistent across multiple observations, and consistent across different data reduction pipelines. Even more damaging for this hypothesis is that the imaging tells the same story. The jets, those million-kilometer structures pointing both toward the Sun and away from it, are a completely independent line of evidence that material really was being expelled in large amounts. You can literally see the mass loss happening in the pictures themselves. The acceleration does not come out of nowhere. It lines up perfectly with what the images show, and the alternative forces simply are not strong enough. Solar radiation pressure on something the size and mass of a 5 to 6 kilometer nucleus at 1.36 AU is roughly 10 to the minus 8 meters per second squared. The measured acceleration is around 10 to the minus 2, a factor of 1 million larger. No known radiative or thermal effect even approaches that level. They are off by orders of magnitude. So while it would be convenient if the acceleration were just a measurement artifact, the evidence strongly suggests it is real, it is correctly interpreted, and it demands a substantial mass loss, a mass loss the images do not show. Another idea is that maybe only a tiny fraction of 3I Atlas was actually active. Perhaps 95% of the surface was inert, buried under dust, rock, or hardened crust, and all the sublimation came from a handful of small vents. That would mirror what Rosetta saw at Comet 67P, where most of the surface was essentially dead and only about 10% produced meaningful activity. It would also explain why the visible jets look so structured and coherent. If everything is coming from a few narrow regions, the gas naturally forms tight jets that can appear larger or wider in long exposure images than they really are. And on paper, this sounds like a neat solution. If only 5% of the surface is active, you only have to heat that 5%. That is roughly 5 square kilometers instead of 98. A much smaller thermal load. A smaller region to power. Maybe that is where the mass came from. Efficient little nozzles blasting material into space. But here is where the idea breaks down. Concentrating activity into small areas does not change how much total mass needs to leave the comet. If the acceleration measurements are correct, and all evidence so far says they are, then billions of tons were ejected. It does not matter whether that material comes from 5% of the surface or 100%. The momentum requirement is the same. And in fact, a tiny, active area actually makes the problem worse. If only 5 square kilometers are responsible for all the outgassing, those patches would have to eject material at impossibly high rates, hundreds of kilograms per second per square meter. That is far beyond what any comet has ever produced, even during extreme outbursts. There is another issue. If the activity were confined to just a few small vents, the jets near the nucleus should look sharply defined and should originate from clear, identifiable points. But the high-resolution images do not show that. The inner coma looks broad and diffuse, not like a bundle of thin, needle-like jets. That suggests the activity is more widespread than the 5% active area idea requires. So while this hypothesis might explain the overall shape of the jets, it does not resolve the central contradiction. You would still need the same enormous mass loss to generate the observed acceleration. Concentrating the activity into smaller areas does not reduce the total. It only demands far more from each individual vent, more than cometary ice can realistically provide. Another possibility is that we are simply getting the timing wrong. Maybe the jets have not been active for 1 to 3 months, the way our calculations imply. Maybe they are much fresher, only a few days old. If that were true, the jets could still reach 1 million kilometers in length, but only if the material were moving 10 times faster than we assumed. Shorter duration, same distance, higher velocity. And if they formed suddenly, just before the November 9th images, they could in principle look identical while requiring far less total mass. It is tempting, because comets do produce transient features. Outbursts flare up and fade away. Jets switch on and off as the nucleus rotates. Some structures appear almost overnight, so perhaps the jets we are seeing only turned on in late October or early November. But the timeline refuses to cooperate. We saw a sunward component, an anti-tail, as early as July 21st in the Hubble images. We saw activity increasing in September. By November 9th, the jets were already large, structured, and extending over enormous distances. On November 11th, they were still there, consistent and continuous. This is not a transient eruption. It is a months-long steady outflow. And if we try to force the only a few days old interpretation, we run straight into physics. To produce million-kilometer jets in 3 days, the material would need to travel at around 4 kilometers per second. That is impossible for thermal sublimation at 1.36 AU. CO2 at those distances produces speeds around 400 to 500 meters per second. Even water vapor tops out around 1 kilometer per second. To reach 4 kilometers per second, you would need temperatures above 2000 Kelvin hotter than a blowtorch, something no comet can achieve through sunlight alone. The jets themselves also give away their age. They are smooth and continuous, not jagged or chaotic the way fresh outbursts often appear. Their curvature and alignment show a steady, persistent flow over long intervals, not a sudden, explosive onset. So the timing was wrong idea collapses under the simplest check. The observations show these features have been present for months, not days. The jets are not new. They have been building and sustained for a long time. There is a final possibility people raise when all the other explanations start to fail. Maybe something else entirely is producing the acceleration. Maybe the push we are seeing is not from normal outgassing at all. Perhaps there is an internal heat source, radioactive decay, or chemical reactions releasing energy from deep inside the nucleus. Perhaps the comet's rotation state is changing in a way that produces a subtle but steady force. Perhaps magnetic interactions with the solar wind are involved. Or perhaps the acceleration is coming from some kind of deliberate propulsion. There are a few natural scenarios people consider. One is radioactive decay. If 3I Atlas contains unusual isotopes, they could generate internal heat. That heat could drive sublimation from the inside out instead of from the surface. Another idea is that if the nucleus is tumbling irregularly, changes in rotation might create small accelerations, something we have indeed observed in a few asteroids. And there is also the possibility of chemical reactions inside the body. Exothermic reactions could release stored energy without needing sunlight, and in theory, dissociation of CO2 clathrates could release additional heat. But each of these natural alternatives breaks down under scrutiny. Radioactive decay is simply too weak. Even relatively young radioactive material only produces about 1 watt per kilogram. Multiply that by 3.3 times 10 to the 13 kilograms. The estimated mass of the comet, and you get roughly 10 to the 13 watts. It sounds huge, but the comet receives around 10 to the 10 watts from sunlight, and even all that internal heat would add only about 0.1%. Nowhere near enough to power the kind of mass loss we are trying to explain. Changes in rotation produce torque, not linear thrust. They affect the spin rate, not the orbit. But the acceleration we see is a translation, a push in a specific direction, not a change in spin. And chemical reactions do not solve the energy budget problem either. Clathrates release energy when destabilized, but they require heating in the first place. They shuffle energy around. They don't create it from nothing. And even if they did, where would this enormous store of energy have come from? Because of all that, some people turn to a non-natural explanation. Rocket propulsion, for example, would immediately resolve the energy shortfall. A chemical rocket produces exhaust at 3 to 5 kilometers per second. An ion engine can produce exhaust between 10 and 50 kilometers per second. Higher exhaust velocity means you need far less mass to produce the same thrust. If the outflow velocity were 10 times higher than cometary sublimation, then instead of 50 billion tons of expelled material, you would need only about 5 billion. And if it were 20 or 30 times higher, you could get by with only a few 100 million tons. This kind of propulsion would also resolve the mismatch between the comet's small surface area and the enormous energy required to power the observed mass loss. You do not need sunlight at all if the energy comes from onboard systems. It would also explain the strange statistics why our second interstellar visitor just happens to be a large, unusually volatile rich object exhibiting anomalous behavior. That transition from 1 in 100 million to deliberate trajectory choice removes the improbability. and it would explain why the nucleus did not fragment despite the huge forces involved. A designed structure with internal reinforcement could easily survive thrust levels that would tear an ordinary comet apart, but this non-natural interpretation carries enormous scientific burden. Extraordinary claims need extraordinary evidence. Before considering anything like propulsion, we have to rule out every natural explanation with high confidence, and we are not there yet. December's spectroscopic observations will be decisive. Chemical rocket exhaust has a completely different spectral fingerprint from natural sublimation. Combustion products, high-temperature ions, or electrically accelerated particles would stand out immediately. An ion engine, for example, produces extremely fast ionized gases with characteristic emission lines. If anything like that were present, spectroscopy would not miss it. And even beyond instrumentation, the alien spacecraft hypothesis demands multiple independent lines of evidence before it becomes scientifically viable. It is a hypothesis of last resort, something to consider only after every natural mechanism has definitively failed. Right now, we are not at that point, but December's observations will tell us very clearly whether we need to revisit this possibility or whether a natural explanation is waiting just beneath the surface. After working through every hypothesis, we can finally step back and see where the evidence is pointing and where it isn't. At this stage, the only explanations that seem capable of reducing part of the discrepancy are ordinary ones, but even they fall short. The most realistic scenario is a combination of factors. Maybe the comet is a little more massive than the first estimates suggested, maybe the jets are somewhat more collimated than they appear in wide-field images, and maybe the dust-to-gas ratio is lower than average. If all three of those things happen at once, the apparent mass loss could shrink from the extreme upper estimate of 50 billion tons to something like 10 or 15 billion. That would help, but even then it doesn't solve the mystery. It only trims the edges. Some ideas can almost certainly be ruled out. Measurement errors are very unlikely. The non-gravitational acceleration has been confirmed independently by multiple orbit determination groups, each using different data pipelines. The idea that the debris has already dispersed doesn't match the historical behavior of comets hundreds of times less mass than this has remained visible for months, and the notion that the jets are sudden, short-lived features contradicts the fact that we have seen sunward structures consistently for months, all the way back to July. Several other possibilities remain open, but only because we need the December observations to test them. The transparent gas idea will rise or fall based on spectroscopy. If gas production is genuinely enormous, CO2 emission bands will reveal it immediately. The fragmentation idea will be settled the moment Hubble compares the nucleus before and after perihelion. And the size hypothesis, whether the nucleus is really 5 to 6 kilometers or something larger, will also be pinned down by those same images. December will answer those questions definitively. And then there is the uncomfortable possibility. If the December spectroscopy shows gas production rates that are modest, say, only 1,000 to 10,000 kilograms per second, far below the 1 to 2 million kilograms per second required to explain the observed acceleration, and if Hubble shows that the nucleus is still intact, still a single coherent object with no signs of fragmentation, and if the non-gravitational acceleration is confirmed at the same strength we see today, then we are left with a genuine, hard anomaly, a mismatch between the observed force and the amount of natural mass loss that could possibly produce it. That is the kind of scenario where natural comet physics begins to run out of room and where alternative explanations, including the last resort possibility of some form of propulsion, would have to be examined seriously. But we are not there yet. We do not have the December data. All we can say is that the stage is set for one of two very different outcomes. In the first outcome, the mystery evaporates. The December images reveal a large debris cloud that was simply low contrast or difficult to resolve earlier. The spectrum shows strong CO2 emission lines, indicating huge gas production. Everything fits. The comet behaves like a natural object with unusual but understandable properties. In the second outcome, the mystery deepens. December arrives and the coma is still modest. The spectrum shows only ordinary gas production. The expected debris cloud has not materialized. The nucleus is still intact, and the acceleration remains real. In that case, Something about 3I Atlas does not fit into natural comet models. The numbers refuse to close. And we are left with a phenomenon that demands explanations we have never had to consider before. Either way, the uncertainty won't last much longer. In just 34 days, we get our answers. December 19th, 2025, mark that date. On that day, 3I Atlas reaches its closest approach to Earth at a distance of 1.798 astronomical units. That's about 269 million kilometers. Still very far, around 700 times the distance between Earth and the Moon, and nearly twice the distance between Earth and the Sunday. You won't see it with your eyes, and you almost certainly won't see it with binoculars. But for telescopes, that distance is close, very close. And even more important, the geometry is ideal, high in the pre-dawn sky for northern observers, well separated from the sun's glare, drifting through the constellation Leo. Perfect conditions for observation. For the next month and a half, early December through mid-January, hundreds of telescopes across the planet will be following this interstellar visitor. Professional observatories, amateur telescopes, space-based instruments. It will become the most concentrated, globally coordinated observation campaign ever organized for an object that came from outside our solar system. Right now, as you listen to this, the planning is already underway. The IAWN, the International Asteroid Warning Network, normally spends its time tracking objects that might threaten Earth. Interstellar visitors are usually none of their concern. But 3I Atlas is unusual enough that the network has assembled a dedicated observing campaign, running from November 27th, 2025, through January 27th, 2026. This isn't casual cooperation. This is scheduled observing blocks at major observatories on 6 continents. This is standardized data sharing, coordinated imaging sequences, and real-time processing pipelines. Across North America, observatories in Arizona, New Mexico, and Texas are on the schedule, including the 4.3-meter Discovery Channel telescope and the 3.5-meter telescope at Apache Point. In South America, Gemini South and the Very Large Telescope Array will participate, along with the Magellan telescopes at Las Campanas. Across Europe, the Nordic Optical Telescope and the Isaac Newton Telescope will watch from the Canary Islands, joined by multiple European Southern Observatory facilities farther south. In Asia and the Pacific, Subaru, Keck, and other high-aperture instruments in Hawaii, along with observatories in Japan, China, and India, will provide coverage across the Pacific night. In Africa, the South African Astronomical Observatory is part of the network. In Australia, the Anglo-Australian Telescope will provide Southern Hemisphere continuity. Taken together, this network creates essentially round-the-clock coverage. When 3I Atlas is setting for observers in North America, it is rising for observers in Asia. When the sky brightens in Europe, darkness falls in Chile or Hawaii. The object will almost never be unobserved, but the most decisive observations won't come from the ground at all. The truly critical data will come from above Earth's atmosphere, from the Hubble Space Telescope and the James Webb Space Telescope. Both have already scheduled multiple observing windows in December, timed specifically to catch 3I Atlas when it is bright, well-placed, and scientifically most revealing. Hubble begins its campaign in mid-December. Between December 15th and 17th, it will take high-resolution images in ultraviolet, visible, and near-infrared light. Then, from December 18th through the 20th, it will use the Space Telescope Imaging Spectrograph, the instrument known as STIS, to collect ultraviolet spectra. After that, from December 22nd to 24th, Hubble will take follow-up images to look for changes over time. These observations will answer several of the biggest questions directly. First, fragmentation. Hubble's resolution is good enough to see pieces separated by as little as 1,000 kilometers. If the nucleus broke into 16 or more fragments during or after perihelion, Hubble will not miss them. Each piece would have its own tiny coma, its own brightness profile, its own distinct motion. This will give us a clean, unambiguous yes or no answer. Second, the size of the nucleus. By comparing the December images with the ones taken on July 21st, We can tell whether the nucleus has shrunk, whether its shape has changed, and whether its brightness has shifted in a way that would indicate stronger or weaker activity. If the comet really expelled tens of billions of tons of material, the nucleus should look different. If it doesn't, that tells us something important. Third, the structure of the coma itself. Hubble's sharp imaging can resolve the architecture of the jets, whether they emerge from small active regions, whether they form arcs or shells from episodic outbursts, whether the shape of the coma reveals rotation or precession. These details matter because they reveal how the comet is venting material into space and whether that venting matches the measured acceleration. And finally, the ultraviolet spectra. UV light shows the fingerprints of the gas. Hubble will be able to detect hydroxyl from water dissociation, atomic oxygen, atomic carbon, atomic sulfur, and the bright blue emissions of ionized carbon monoxide, the species CO+. From those lines, scientists can calculate the actual gas production rates. If something extraordinary happened at perihelion, the UV spectra will make it obvious. The James Webb Space Telescope will provide the other half of the picture. Webb observed 3I Atlas once before perihelion on August 6th. The December sessions are designed to reveal how dramatically things have changed since then. Between December 12th and 14th, Webb will use its near-infrared spectrograph, NIR-SPEC, to measure the abundance of volatiles, including CO2, carbon monoxide, water, methane, and other species that emit in the infrared. Then, from December 19th through the 21st, Webb will use its mid-infrared instrument, MIRI, to probe deeper into the thermal emission from the dust and from the warm surface of the nucleus. Together, Hubble and Webb will give us the highest precision look at an interstellar comet that humanity has ever achieved. If there is a natural explanation for the strange behavior of 3I Atlas, these instruments will find it, and if there isn't, then what they reveal in December may force us to rethink what we think we know. The James Webb Space Telescope will give us the most decisive measurements of all. Webb's infrared spectroscopy can directly measure the production rates of the gases coming off the comet, especially CO2, the dominant volatile in 3I Atlas. Back in August, before perihelion, Webb measured a production rate of about 150 kilograms per second. If perihelion triggered the kind of enormous mass loss implied by the post-perihelion acceleration, that number should skyrocket in the December data. We should see 10,000, 50,000, even 100,000 kilograms per second or more. If instead the rate is still only a few thousand kilograms per second, that would tell us the comet's activity has remained modest. And if the gas production is modest, then the enormous mass loss estimates from the jet calculations cannot be correct. The mystery would deepen. Webb will also measure the water output directly by detecting the infrared lines of H2O. In August, the total gas production was around 150 kilograms per second, and because 87% of that was CO2, the water component was only about 20 kilograms per second. If the perihelion passage caused a natural increase in sublimation, both CO2 and water should rise together. If water does not increase, or if it increases only slightly, that would be another sign that the energy budget does not match what we expect from normal sublimation. Another crucial piece of information comes from temperature mapping. Webb can measure the surface temperature across different regions of the nucleus. If there are hotspots, localized patches, much warmer than their surroundings that would indicate active sublimation vents. If the entire surface is uniformly warm or uniformly cool, that would argue against the idea of extreme, localized mass loss. Webb will also reveal the thermal gradient, how quickly the comet is cooling after perihelion, and whether any part of the surface retains heat in a way that natural models cannot explain. Webb's mid-infrared instrument, MIRI, will analyze the dust. It will tell us what the dust is made of: silicates, organic compounds, or even crystalline ice. It will reveal the particle size distribution, whether the comet is shedding fine, micron-scale dust, or larger grains. And from the thermal emission, Webb can calculate the dust production rate. All of these measurements feed into a single, crucial question: how much mass is actually leaving the comet? And this is where the numbers give us a clean test. If the total gas production in December is only 1,000 to 5,000 kilograms per second, then over 1 month the comet would lose about 2.6 billion kilograms, roughly 2.6 million tons. That's perfectly consistent with modest, ordinary cometary behavior and wildly inconsistent with the 5 to 50 billion tons implied by the jets. In that scenario, the mystery doesn't go away. It becomes harder to explain. If the production rate is around 100,000 kilograms per second, then the comet would lose about 2.6 times 10 to the 11 kilograms over a month, about 260 million tons. Still far short of 5 billion, but closer. A natural explanation would remain on the table. But if Webb measures something astonishing, 1 million or even 2 million kilograms per second, then the mass loss over a month would reach 5 billion tons. That would perfectly match the jet calculations. The natural explanation would be confirmed. The energy budget, the acceleration, the coma size, they would all fit. There is no ambiguity in this. Webb's spectroscopy gives us a direct, quantitative measurement of the outgassing rate. December's data will tell us exactly how much mass the comet is losing, and from that, we will know which side of the mystery we fall on. The largest ground-based telescopes on Earth will supply the other half of the picture. Space telescopes see what? The atmosphere blocks. The giant mirrors on the ground can collect enormous amounts of light with unmatched spectral detail. In Chile, the Very Large Telescope will use its X-shooter spectrograph, which can record ultraviolet, visible, and near-infrared wavelengths all at once. That means we can measure the classic comet tracers simultaneously: the cyanide radical, the carbon molecules C2 and C3, the NH2 ammonia fragment, and even the faint emissions from atomic sodium and potassium released from dust grains. X-shooter will also record the Doppler shifts of these lines, letting us calculate the speed of the gas as it flows away from the nucleus. On Mauna Kea in Hawaii, the Keck Observatory will use its high-resolution spectrometer, HIRES. This instrument can measure individual emission lines with exquisite precision, so precisely that it can determine gas velocities to within 1/10 of a kilometre per second. This is the crucial test. If the gas is flowing at roughly 0.4 kilometers per second, maybe up to 0.8, that is exactly what we expect from natural thermal sublimation. But if Keck measures gas moving at 2, 3, or even 5 kilometers per second, that is far too fast for normal comet physics. That would imply the gas is being actively accelerated by some other mechanism. And if Keck were to find velocities in the 10 to 50 km per second range, that would be completely impossible for chemical outgassing. Only technologies akin to ion propulsion would reach those speeds. Gemini, North and South, in Hawaii and Chile, will map how gas production varies across the coma. Their spectrographs can build two-dimensional images showing which regions are emitting which molecules, and how those regions change over time. This will reveal whether the activity is spread across the surface or confined to narrow jets. And the Subaru telescope, also on Mauna Kea, will use high-resolution imaging spectroscopy to create literal composition maps of the coma, showing where specific molecules are concentrated and how they disperse as the gas expands. Together, these measurements all converge on a single question: how fast is the gas actually moving? If Keck and the other large telescopes measure gas speeds of around 0.4 to 0.8 kilometers per second, then the outflow is perfectly consistent with natural sublimation of CO2 and water ice. In that case, the comet behaves like an ordinary, if somewhat unusual, interstellar visitor. Any mismatch in the mass calculations must come from our assumptions about density, jet geometry, or viewing angle. But if the measured velocities fall in the range of 2 to 5 kilometers per second, we move into territory that natural comet physics cannot explain. Those speeds are too high for sunlight-driven sublimation. They resemble the exhaust velocities of chemical rockets. That would be a major anomaly, and if any instrument measures gas moving at 10 to 50 kilometers per second, the implications would be profound. No chemical process can achieve that. Only ion engines and plasma propulsion reach those regimes. Such a result would have no precedent in cometary science and would demand an explanation far outside the familiar models. This is why December's velocity measurements are so critical. They provide a clean, objective test. No assumptions about jet width, no need to guess the dust-to-gas ratio, no uncertainties about the nucleus mass, just the raw speed of the gas. And that speed alone can confirm or rule out entire categories of hypotheses. Every telescope in the campaign will be searching for one thing above all else: signs of fragmentation. If the nucleus of 3I Atlas truly lost 15 to 50% of its mass, as some calculations suggest, then it should have shattered into many pieces. And if that happened, the evidence will be unmistakable. Fragmentation leaves a very specific signature. Instead of a single bright condensation at the center of the coma, you begin to see multiple points of light, each surrounded by its own miniature coma. These points slowly drift apart, separating by thousands of kilometers per day. Some brighten, some fade. Each follows its own path as pieces spin, tumble, and sublimate at their own rates. Over weeks, a shattered comet looks like a loose swarm rather than a single nucleus. Hubble's sensitivity is perfect for this test. It can detect fragments as small as 100 meters across, as long as they are producing even a small amount of gas. And its resolution is high enough to distinguish pieces that are more than 1,000 kilometers apart. If 16 or more fragments exist, the number predicted by Abraham Loeb's mass loss models, Hubble will not miss them. It will count every one. Throughout December and January, astronomers will perform time series monitoring, repeated imaging every 2 or 3 days. This allows them to track the motion of any fragments, measure how fast they are separating, and compare those speeds to what tidal disruption and rotational breakup models predict. If 3I Atlas truly lost that much mass, the fragments should now be tens of thousands or even hundreds of thousands of kilometers apart. Loeb's estimates suggest pieces moving at 10 to 100 meters per second. After a month and a half, that would produce separations between 40,000 and 400,000 kilometers. Such spacing would be obvious, and that leads to a simple prediction. If those pieces exist, Hubble will see them. If they do not appear, then something is very wrong. Because if no fragments are found, only 3 possibilities remain. Either the comet did not lose anything close to the mass required by the measured acceleration, which contradicts the orbital data, or the nucleus is far stronger than a typical comet, with a structural integrity more like a solid monolith than a fragile rubble pile. Or, in the most unconventional interpretation, the nucleus is not a natural object at all. While Hubble searches for fragments, other instruments will focus on the dust. Dust carries critical information. Its brightness, its color, and its polarization all reveal how much material the comet is shedding and what that material is made of. Photometry will measure the brightness of the coma in multiple wavelengths: ultraviolet, blue, green, red, and near-infrared. The colors tell us the composition of the grains. The rate at which the brightness changes reveals how fast dust is being produced. Polarimetry, which measures how sunlight becomes polarized when it scatters off dust grains, can determine the particle size distribution. Different grain sizes polarize light differently. That signature makes it possible to infer whether the coma is full of fine powder, larger aggregates, or something in between. Thermal infrared observations add another layer. Dust grains absorb sunlight and re-emit the energy as heat. By measuring that thermal glow, astronomers can estimate the temperature and therefore the average grain size. They can also determine the dust production rate. All of these measurements converge on a simple test. If 3I Atlas produced 5 billion tons of gas with a typical 10% dust-to-gas ratio, then the comet should have released roughly 500 million tons of dust. That kind of release would create a bright, extensive dust tail, long, dramatic, and impossible to miss. In that case, the natural explanation works. But if dust production is far lower, less than 100 million tons, then something unusual is happening. Low dust could mean exceptionally gas-rich material. It could mean a crust preventing dust from escaping, or it could mean the gas production itself was smaller than expected. If both gas and dust are low, the mass loss problem disappears. But if gas is high and dust is low, the comet becomes extremely unusual. Amateur astronomers will also play an important role. Anyone with an 8 to 12-inch telescope can contribute real data. By measuring the comet's brightness night after night and submitting those magnitudes to the global databases maintained by the Comet Observation Database and the Minor Planet Center, amateurs help track changes in activity. Precise astrometric measurements refine the orbit and test whether the non-gravitational acceleration is continuing. And long-exposure images taken from dark skies can reveal subtle changes in the tail and coma structure, filling in the gaps between professional observations. In other words, December is not just a scientific campaign. It is an all-hands, global effort to understand whether 3I Atlas is behaving like a normal, if extreme, interstellar comet or something entirely different. Thousands of amateur astronomers will be watching. Their combined effort creates a nearly continuous stream of observations that fills the gaps between the scheduled professional telescope sessions. This global network of observers allows us to track every change in the comet's appearance, brightness, and position. It is the kind of distributed, round-the-clock coverage that no single observatory could accomplish alone, but interpreting the data will take time. This is not like getting lab results back in an hour. Astronomical data analysis follows a timeline. In the immediate stage, within hours to a few days, the raw images will become available. Quick-look analyses will begin. Astronomers will ask simple but crucial questions. What do we see? Are there fragments? Are there jets? Did an outburst occur? The major features will be identified rapidly, but only at a superficial level. In the short-term stage, within a few weeks, the serious work begins. Spectroscopic data must be carefully calibrated. Gas production rates will be calculated. Velocity, measurements will be refined. Preliminary composition analysis will be completed. By this point, the first reliable numbers start to emerge. The medium-term stage unfolding over several months brings the most detailed results. Scientists will build full physical models of the coma structure. They will compare the post-perihelion behavior to the pre-perihelion data. They will complete a comprehensive analysis of the composition. Peer-reviewed papers will begin to appear. Here is what we will know by early January of 2026. We will know whether fragments exist, a simple yes or no. We will know approximate gas production rates, at least to the correct order of magnitude. We will have rough velocity estimates, and we will know whether a massive debris cloud exists or not. By March or April of 2026, the deeper answers will arrive. We will have precise gas production rates. We will have accurate velocity measurements. We will have detailed composition results. And we will be able to say with confidence whether natural explanations fully account for the comet's behavior. All of this leads to three possible scenarios. Scenario 1. A natural comet is confirmed. In this scenario, the observations show gas production rates between 10,000 and 100,000 kilograms per second or higher. The coma expands to a diameter of 1 to 5 million kilometers. The dust tail stretches for millions of kilometers. Gas velocity is between 0.4 and 0.8 kilometers per second, exactly what thermal sublimation predicts. There may even be some fragmentation, perhaps 5 to 20 pieces. In this interpretation, 3I Atlas really did lose billions of tons through natural sublimation. The apparent paradox in the earlier calculations would be explained by a combination of factors: underestimating the comet's size or mass, overestimating the required active surface area, and missing the debris cloud in early Embrius, November, due to viewing geometry and dispersal effects. In this scenario, the comet turns out to be extreme, but not anomalous. A carbon dioxide-rich composition can produce unusual behavior, but all of it remains within the bounds of natural physics. The scientific impact would be significant. Models of comet sublimation for carbon dioxide-dominated bodies would be updated. The result would confirm that interstellar objects behave according to the same laws of physics as comets from our own solar system. And we would gain new insight into the building blocks of planets in other star systems. The case would be considered closed, and the predicted response from Avi Loeb, the astrophysicist who raised many of the early questions, would be to acknowledge that the natural explanation fits the data. He would emphasize that asking bold questions is part of how science progresses, and then move on to studying the next interstellar visitor. Scenario 2. Ambiguous results. In this scenario, December data gives us a mixed picture, not clearly natural, not clearly anomalous. The observations show moderate gas production, somewhere between 1,000 and 5,000 kilograms per second. The coma grows larger than it appeared in November, expanding to a size between 200,000 and 500,000 kilometers across. There is some tail development, though not dramatic. Gas velocity clocks in between 0.5 and 1.0 kilometers per second, slightly higher than the standard thermal range, but still explainable without invoking anything exotic. And crucially, no clear fragments are detected. The interpretation is that significant mass loss did occur, but nowhere near the extreme levels suggested by the early jet analysis. The jets might have misled us, perhaps they were more tightly collimated than we thought, giving them a smaller physical cross-section, or they may have been produced by a brief, intense outburst rather than a sustained month-long flow. Or perhaps the geometry of the images created an illusion that made them appear larger and denser than the physical quantities actually required. In this scenario, the total mass lost would be on the order of 100 to 500 million tons. That is large, but not catastrophic. A comet of 30 billion tons could easily survive losing less than 5% of its mass. That would explain why the nucleus remained intact. The scientific impact of this scenario is important but not revolutionary. It highlights the uncertainties that come with remote observation. It reminds us that analysing jets from a single viewing angle can lead to overestimates. And it underscores the need for direct spacecraft missions to interstellar visitors because telescope data alone can only push us so far. The community response would be moderate. Most scientists would conclude that the natural explanation still holds. Some lingering questions would remain, especially about how jets can appear deceptively large. Avi Loeb would likely point out that the anomalies are not fully resolved and that parts of the data still resist tidy explanations. The debate would continue, but with less intensity than before. Scenario 3. Anomaly confirmed. This is the scenario where the numbers refuse to add up, where something truly does not fit our current understanding of comet physics. In this case, the observations show very low gas production, less than 1,000 kilograms per second. The coma remains modest, roughly 100,000 to 200,000 kilometers across, almost unchanged from its appearance in November. There is minimal tail development. If gas velocity can be measured at all, it exceeds 2 kilometers per second, which is too fast for thermal sublimation at that distance from the Sunday. And once again, there is no fragmentation. The nucleus remains a single, intact object. Even more striking, the nucleus size remains unchanged from the July measurements. No shrinkage, no erosion, no major surface loss. The interpretation becomes unavoidable. The non-gravitational acceleration is real. That part is confirmed. But the debris that should account for the acceleration is missing. Nothing in the images or spectroscopy shows the giant cloud of gas or dust that would be required to generate the observed push. This creates a genuine paradox. Something pushed the comet, but the usual mechanism outgassing did not create that push. So what is left? This is not a matter of speculation or wishful thinking. It is a direct contradiction between two independently measured quantities. First, the trajectory shows a measurable acceleration. Second, the observable mass loss is far too small to explain that acceleration. If scenario 3 is what the December data reveals, then we are looking at an object whose behavior cannot be fully explained by standard comet physics. And at that point, the scientific community must confront the central question. What else, besides normal outgassing, could accelerate an interstellar object? Possible explanations if scenario 3 occurs. If December's data places us in scenario 3, low gas production, no debris cloud, an intact nucleus, but a very real non-gravitational acceleration, we are forced into a narrow set of possible explanations. Most are natural, but all are highly unusual. 1. Highly unusual outgassing geometry. One idea is that the comet released gas in a way we have never seen before. This would include possibilities such as subsurface jets, escaping through tiny vents, sudden violent bursts that happen between observations, extremely narrow, almost laser-like beams of gas. These mechanisms could create strong thrust with very little visible debris. Problem: nothing like this has ever been observed in any comet. Sustaining the required thrust for several weeks without leaving a trace would be unprecedented. 2. Exotic ice. Chemistry. A second idea is that the comet contains exotic ices with stored energy. Examples include carbon dioxide clathrates releasing energy, phase transitions between different states of ice, chemical reactions inside the nucleus. These could produce bursts of gas strong enough to alter the comet's motion, but they require physics that has never been demonstrated at the needed scale. 3. Strange internal structure. The nucleus may have an internal structure unlike any known comet. Possibilities: a solid metallic or rocky core, a thin ice shell covering a rigid frame, unusual rotational changes creating momentum transfer, but rotation creates torque, not continuous linear acceleration for several weeks. This does not match the observed behavior. 4. The non-natural explanation: active propulsion. This is the idea considered only if every natural explanation fails. Active propulsion. A chemical rocket produces exhaust speeds between 3 and 5 kilometers per second. That instantly reduces the propellant needed by a factor of 10. 50 billion tons becomes 5 billion tons. 5 billion tons becomes 500 million tons. An ion drive produces exhaust speeds between 10 and 50 kilometers per second, reducing propellant by a factor of 100. From a physics standpoint, propulsion solves the energy mismatch, but it carries a massive scientific burden. It is an extraordinary claim. What would be required to seriously consider a non-natural explanation? Missing debris is not enough. An intact nucleus is not enough. Even strange acceleration is not enough. We would need positive evidence, such as 1. Exhaust speeds greater than 2 km per second, measured through spectroscopy. Thermal sublimation cannot reach that speed. 2. Chemical signatures inconsistent with natural ices. For example, combustion products, unusual ionization, molecules not created by sunlight. 3. Directional thrust, acceleration, changing in a pattern unrelated to rotation or sunlit orientation. 4. Geometric structure, shapes too regular or symmetric to be natural. 5. Multiple independent anomalies, not just one oddity, but a chain of them. 6. Scientific consensus that no natural explanation works, only after months of modelling, cross-checking, and review. Only then does the discussion move from unusual comet to possible engineered object. Even then, the preferred interpretation would still be, we have discovered a new kind of comet physics, and only last, it might be artificial, scientific impact, major astronomy news across the entire world, intensive modelling efforts to search for a natural explanation, calls for a dedicated spacecraft mission to chase and study the object, planetary defense protocols re-evaluated, astrobiology community becomes heavily involved, public fascination reaches its highest possible levels, Avi Loeb's predicted response, a clear "I told you so" moment, calls for immediate follow-up observations and a spacecraft interception, argues that a technological hypothesis must now be taken seriously, pushes the Galileo project to monitor all future interstellar passes, visitors if scenario 3 occurs, if 3I Atlas proves truly anomalous, if the comet shows sustained acceleration with almost no mass loss, no debris cloud, and no fragmentation, the scientific community will immediately call for a spacecraft mission. 3I Atlas is moving extremely fast, about 40 kilometers per second relative to Earth after perihelion, and it will accelerate as it leaves the inner solar system. To intercept it, a mission must launch very soon. Mission feasibility launch window. From now through mid-2026. Earlier is much better. Every month of delay increases the required velocity dramatically. Delta V required. Between 50 and 80 dramatic kilometers per second, depending on the trajectory. This is far beyond conventional chemical rockets' flight time. Between 5 and 10 years, depending on propulsion and gravity assist options. Technologies needed: high-power solar electric propulsion, planetary gravity assists, potentially nuclear thermal or nuclear electric propulsion for the most fast, aggressive trajectories. Precedent: ESA's Comet Interceptor. The European Space Agency has a mission called Comet Interceptor, launching in 2029. It is designed to wait in space and intercept the next interstellar visitor. But can it chase 3I Atlas? Problems. Launches in 2029, far too late, would require an enormous velocity change to catch the comet. By the early 2030s, the comet will be more than 50 astronomical units from the Sun. At that distance, it will be extremely cold and mostly inactive. Conclusion: Comet Interceptor cannot reach 3I Atlas. Alternative: a fast-tracked dedicated mission. If 3I Atlas is confirmed anomalous, the world would likely attempt a rapid development mission. Possible timeline: design phase 2026 through 2027, build phase 2027 through 2028, launch 2028 or 2029, arrival between 2033 and 2038. By arrival, the comet would be 80 to 100 astronomical units from the Sun. It would be very cold, mostly inactive, but still scientifically priceless. What a spacecraft could measure? 1. Direct mass measurement. Using the gravitational pull on the spacecraft, finally settling the mass loss paradox. 2. Surface composition, close-range infrared and ultraviolet spectrometers. 3. Internal structure, radar, tomography, thermal probes, or seismic sensors. 4. Magnetic field. Natural comets have no intrinsic magnetic field. Its detection would be extraordinary. 5. Shape and rotation, high-resolution imaging revealing geometry, symmetry, or engineered structure. 6. Sample, return, ambitious. A return capsule could bring dust or surface particles back to Earth. A spacecraft mission would answer the ultimate question: natural or not? Cost: roughly $1 to $2 billion. Political will depends entirely on how strange the December observations are. If December shows Scenario 1 or Scenario 2, a mission is unlikely to get funding. If December shows Scenario 3, NASA, ESA, and other agencies would seriously consider an emergency fast-track mission. How you can participate: no PhD required. You do not need a doctorate or a giant observatory. Anyone can follow along or contribute. Follow live updates from Virtual Telescope Project live-streamed observations, Sky and Telescope Magazine weekly updates, Space.com, regular news coverage, Avi Loeb's Medium blog, scientific commentary, NASA's 3I Atlas page, official mission data. If you own a telescope 8 inches or larger, photograph 3I Atlas yourself. Submit brightness measurements to the COBS database. Contribute astrometry to the Minor Planet Center. Join the global network of amateur observers. If you do not have observing equipment, watch live streams during key December windows. Follow the hashtag #3IATLAS on social media. Join astronomy forums for real-time discussion. Participate in Citizen Science by ISA projects that accept public volunteers. Key dates to watch: December 15th through 17th, Hubble High-Resolution Imaging. December 18th through 20th, Hubble Ultraviolet Spectroscopy. December 19th, Closest Approach to Earth. December 19th through 21st, James Webb Infrared Spectroscopy. December 22nd through 24th, Hubble Follow-Up Imaging. January 5th through 10th, ground-based spectroscopy campaigns reach maximum coverage. Late January. First scientific results expected. How to stay informed. Set calendar reminders for the key December dates. Follow leading researchers on social media. Subscribe to reliable astronomy news outlets. This is science unfolding in real time. You can literally watch the mystery evolve day by day. A personal note: I have spent weeks researching this, reading scientific papers, running my own calculations, cross-checking every available source, following the arguments from both sides. And I will be honest with you, I do not know what December will reveal. My intuition says Scenario 2 results that lean toward a natural explanation but still leave us with unresolved questions. The math says Scenario 1 or Scenario 3. Either the natural physics works cleanly or it fails completely. The scientist in me says, pause. Wait for real data. Do not jump to conclusions. Let the observations speak, but the human in me hopes for scenario 3, not because I want extraterrestrial technology, but because I want a real mystery, something that challenges our assumptions, something that forces us to rethink and rebuild our models, something that pushes science forward. Either way, natural or anomalous, 3i Atlas has already achieved something remarkable. It made us pay attention, it made us question our assumptions, it made us think deeply about what is possible and what might not be. This is exactly what science is meant to do. Now step back, zoom out, look at the bigger picture. Because this story is not just about a single object. It is about a new era in how we explore the universe. Before October 2017, we had never confirmed an interstellar object entering our solar system. We always knew they must exist. Every forming solar system ejects planetesimals. Billions of stars eject billions of icy bodies. Interstellar space should be full of wandering debris, and yet for centuries we had never actually seen one, not with confidence, not with clear data. Then came Oumuamua, October of 2017, the first confirmed interstellar visitor, strange, elongated, tumbling chaotically, showing non-gravitational acceleration without any visible coma. It ignited a debate that has continued for more than 8 years. 2 years after that came 2i Borisov, August of 2019, the second visitor, reassuringly normal, a textbook comet. It looked like a comet, behaved like a comet, and contained familiar ices, proof that not all interstellar objects are exotic or anomalous. 6 years later came 3i Atlas, July of 2025, the third visitor, comet-like, yet marked by unusual features, too large, too well aligned, unusually rich in CO2, and perhaps losing far more mass than physics comfortably allows. 3 objects in 8 years. That alone tells us something profound. We are detecting these interstellar travelers now because our surveys have finally become sensitive enough. The Vera Rubin Observatory, formerly known as LSST, entered full operation in 2025. Its 8.4-meter mirror and 3.2 gigapixel camera can image the entire visible sky every few nights. A true revolution in sky monitoring. Astronomers expect Rubin to detect dozens of interstellar objects every year, possibly hundreds if they are more common than early models suggested. Both comet-like objects with comas and asteroid-like objects without them. Wanderers from many different pontes, stellar populations, young stars, old stars, and distant regions of our galaxy. Within a single decade, we may build a catalogue containing 100 to 500 interstellar visitors. At that point, we will finally have the statistics we need. Right now, with only 3 detections, we cannot draw solid conclusions. Oumuamua was strange. Does that mean half of all interstellar objects are strange? Or was it a 1 in 100 outlier and we simply began with an oddball? 2i Borisov was ordinary. Does that mean most interstellar visitors are ordinary? Or are ordinary ones simply easier for us to detect? 3i Atlas is ambiguous. A comet, yes, but an unusual one. Does it represent a common subclass? Or is it yet another outlier, surprising us in a different way? Once we have a sample of 100 interstellar objects, we can finally answer the big questions. Size distribution. Are most of them small on the order of 100-meter scale, like Oumuamua? Or are giant bodies 10-kilometer scale, like 3i Atlas, actually common? This reveals how planetesimals form in other stellar systems. Composition distribution. What fraction are rich in water? What fraction are rich in CO2? What fraction are dominated by CO ices? These details map the temperature gradients in other protoplanetary disks and reveal the diversity of planetary system architectures. Activity levels. How many protoplanetary temperature gradients show active comet behavior? Comas, tails, jets. How many are inert asteroid-like rocks with no volatiles left? This tells us how well these objects retain their ices and how they were thermally processed before being ejected into interstellar space. Velocity distribution. Do most come in slowly from nearby stars? Or do many arrive at high speed, launch from distant regions of the galaxy? This helps us understand the kinematic structure of the Milky Way. Trajectory distribution. Are they truly random in approach angle, or do they arrive preferentially from the direction of the galactic plane? This tells us where in the galaxy most material gets ejected during planet formation. Weirdness distribution. What fractions show anomalies like the non-gravitational acceleration of Oumuamua? How many behave as unusually as 3I Atlas? This tells us whether such oddities are simply natural variations or genuinely rare phenomena. Once we know, have statistics, the strange ones stand out. If 100 objects show normal, thermal outflow speeds around 0.4 kilometers per second, and one single object shows 5 kilometers per second, then that one is a true anomaly. But if 50 out of 100 show 3IATLAS level weirdness, then weird is actually normal for interstellar visitors. If interstellar objects are common if they constantly pass through every star system, including ours, then they form a natural mechanism for transporting material across the galaxy, possibly including biological material. The current estimates go like this. The total number of interstellar objects in the Milky Way, larger than 1 kilogram, is on the order of 10 to the 26. The rate passing through our solar system is roughly 10 per year for smaller 100-meter scale objects, and about 1 per decade for kilometer scale objects. Over the 4.5 billion year history of Earth, roughly 450 million interstellar objects larger than 1 kilometer have passed near our planet, and countless smaller ones, far too many to tally. This is why some researchers seriously consider panspermia, the idea that life, or the building blocks of life, might travel from star to star on natural interstellar debris. Some of those interstellar objects probably did impact Earth, not just drifted past, but actually struck our planet and deposited their material into Earth's environment. That means Earth has received samples from hundreds to thousands of other stellar systems. Water, organic molecules, and possibly even microorganisms from faraway stars have arrived here. There has been a constant, low-level exchange of material between star systems for billions of years. And that raises profound questions. Is Earth's water purely local? Or did part of it come from interstellar comets that slammed into our planet during the late heavy bombardment roughly 3.9 billion years ago? Are the organic molecules that helped seed early life entirely terrestrial? Or are some of them foreign imports, materials formed around distant suns that later mixed into Earth's chemistry? We have long imagined Earth's biosphere as isolated, evolving in its own bubble. But if interstellar visitors have been delivering material for billions of years, then Earth is not isolated at all. It is part of a galactic ecosystem. 3I Atlas itself might contain organic compounds that formed around another star 8 to 10 billion years in the past. If even a tiny fragment of it were to impact Earth or Mars, unlikely, but not impossible, those ancient organics would join our own environment. Even if living organisms cannot survive the harsh radiation of interstellar space, the building blocks of life can. Amino acids, nucleobases, lipids, simple organics that chemistry naturally produces in many environments. They could be scattered throughout the Milky Way, carried on comets, asteroids, and icy fragments drifting between stars. This makes the origin of life less of a lucky accident on one world, and more of an inevitable outcome of organic chemistry spread across the galaxy. And then we reach the question that most astronomers avoid, not because it is impossible, but because it is uncomfortable. If civilizations arise, and if even a few of them develop interstellar technology, what is the probability that we might detect one of their craft? Avi Loeb argues that we should not ignore this possibility. Instead, he says we should actively search for signs of technology in interstellar visitors, because if any civilization anywhere sends even a single probe, our surveys are now sensitive enough to notice the anomalies. The argument goes like this. First, civilizations might use interstellar objects as transportation. These objects are already drifting between stars at high speed. A civilization could intercept one, anchor to it, and use it as a free ride. Science fiction has long imagined hollowed-out asteroids serving as generation ships, slowly carrying passengers from one star to another. Second, a civilization might build autonomous probes instead. Self-replicating von Neumann probes could copy themselves from raw materials and spread from star to star. In theory, a single technological species could explore the entire Milky Way in roughly 10 million years. If even one civilization in the galaxy built such probes at any time in the past, they could be everywhere by now. Third, if that is even remotely plausible, then we should look for signatures, things that natural comets and asteroids do not do. Geometric shapes too regular to form naturally, non-thermal emissions such as radio bursts or laser flashes, anomalous accelerations, the kind seen in Oumuamua, unusual compositions like manufactured alloys, orbital corrections that look like active guidance. Even if only a tiny fraction, say 0.1% of interstellar objects were artificial, and if the Rubin Observatory ends up detecting about 50 such visitors per year, then we would expect to encounter one technological object roughly every 20 years. That alone makes the search worthwhile. This is why the Galileo project, founded by Avi Loeb, is building dedicated observatories specifically to monitor interstellar visitors. These observatories will track new interstellar objects as soon as they appear, look for anomalous behavior, collect high-resolution optical, infrared, and radio data, search for signals or signatures that do not fit natural models. Most astronomers think this is unnecessary. They argue that natural explanations have worked for everything we have observed so far. They see the search for alien technology as scientifically valid, but probably futile, a detour from mainstream astronomy, not a priority. Loeb counters that the cost is low and the potential payoff is enormous. Even a negative result, finding no technological signatures, would be scientifically valuable. If we study 10,000 interstellar objects and none show signs of artificial origin, we can say with confidence that fewer than 1 in 10,000 are technological. That is real data. That constrains the prevalence of advanced civilizations. And this is why, regardless of what December reveals, 3i Atlas has already changed the conversation. It forced the scientific community to think differently about interstellar visitors, to rethink our assumptions, and to take seriously the possibility, however remote, that not everything drifting between the stars is just rock and ice. Before 3i Atlas, interstellar objects were curiosities. Oumuamua sparked debate, but many scientists dismissed its oddities. Most astronomers were not thinking seriously about interstellar visitors at all. After 3i Atlas, everything changed. Major observatories are devoting real observing time. International teams are coordinating around the clock. Dozens of papers are being written, analysing every detail. Public engagement is at an all-time high. Conversations now include technology, biology, and planetary formation, all triggered by one object, a comet that might be perfectly natural, or might be something unusual. If it turns out to be natural, we learn that CO2-rich comets from other star systems can behave in strange ways. Our models of planet formation chemistry get updated. We become prepared for future visitors with extreme or unfamiliar milia compositions. If it turns out to be anomalous, but still natural, we might discover brand new physics of cometary behavior. We may need to rethink sublimation models from the ground up. We could uncover processes that no comet in our own solar system has ever displayed, if it turns out to be 9. Technological, extremely unlikely, but not impossible. Everything changes. It becomes the first proof of extraterrestrial intelligence. It forces a paradigm shift in how humanity understands its place in the cosmos. And the truth is, even the first 2 outcomes are scientifically priceless. The third would be historically epoch-defining. Let me share something personal. I'm writing this in mid-November of 2025. By the time you are watching this, December's observations might already be in. The mystery might be solved. But right now, as I record this, as I run the calculations, as I check every number, I genuinely do not know what we will find. And that uncertainty is electrifying. This is what drew me to science. Not the answers, the unknowns. Moments when the universe presents a genuine mystery and says, "Here, figure this out." Most science is incremental. You refine a model, you improve a measurement, you add a detail to a detail. But every a few years, Something arrives that is different. Something no one fully understands. Something where experts disagree. Something where the textbook answer may turn out to be wrong. 3i Atlas is one of those moments. I have read Avi Loeb's papers. I have read the counter-arguments from other astronomers. And I have run the numbers myself carefully, repeatedly, to make sure the math is solid. And it is. The observations are real. The calculations are real. The contradictions are real. Something does not add up. Either our observations are incomplete possible, or our models are incomplete possible, or 3i Atlas is doing something that no other comet has ever done also possible. We will know soon. And when we do, I will update this. I will break down the December data. I will explain exactly what the astronomers found and what it means. But until then, we wait. We watch the pre-dawn sky. We follow the observations one by one. We stay present as this unfolds. We are living through a moment in scientific history. Whether it ends up in textbooks as the comet that revealed the chemistry of distant star systems, or the object that made us question everything, we will remember what it felt like to stand here, right now, when the answer was still unknown. November 15th, 2025. A comet from another star drifts through our solar system, carrying a secret. The mathematics say it lost 5 to 50 billion tons of material, ejected violently, stripped away by solar heating during its closest approach to our Sunday. The physics demands it. Conservation of momentum does not just suggest this, it requires it. Not as a hypothesis, but as a consequence of laws that have never failed in more than 300 years of testing. The observations confirm it. Jets spanning millions of kilometers, acceleration measurable across many months of tracking, brightening that suggests catastrophic activity, a blue glow that screams, massive CO2 breakdown. And yet, the debris is not there. The November 11th images from one of the world's best telescopes, analysed by two of the world's most experienced comet observers, show a single, intact nucleus surrounded by a modest coma. Not the shattered remains of a comet that explosively lost half its mass. Not the massive debris cloud that should fill millions of cubic kilometres. Not the fragments that should be separating at kilometres per second. Just a comet, looking almost normal. So where did those 5 billion tons go? There are three possibilities. Possibility 1. The debris is there, but we are missing it too diffuse, too transparent, too spread out to detect. The December observations, with better instruments, reveal the cloud we expected all along. Mystery solved. Natural explanation confirmed. We learned that interstellar comets can hide their mass loss better than we thought. Possibility 2. The debris was never there. The mass loss calculations were wrong. The jets were illusions or short-lived bursts we misunderstood. The acceleration has another explanation. December shows only modest activity, and we realize we overestimated everything. Embarrassing, but scientifically valuable. Possibility 3. Something else is happening. The acceleration is real. The jets were real, but normal comet physics does not explain them. December shows low gas production, an intact nucleus, no debris cloud, and we are forced to consider that 3i Atlas operates by principles we do not yet understand. Maybe natural but unknown. Maybe technological but unlikely. But undeniably, a real anomaly. A comet that does not follow the rules. I do not know which is true. In 34 days, we will start to find out. Hubble will study this ancient wanderer. The James Webb Space Telescope will measure CO2 production with precise spectroscopy. The Keck Observatory will measure gas velocities to determine whether the activity is thermal sublimation or something else. The data will arrive, the analysis will happen, the papers will be written, and we will either solve the mystery or deepen it. Avi Loeb, whose reputation is on the line because he argues we should take anomalies seriously, wrote something that stayed with me. The foundation of pioneering scientific research is the humility to learn rather than the arrogance of expertise. He is right. Science works best when we admit what we do not know, when we follow the data even if it leads somewhere uncomfortable, when we question our assumptions. But science also requires skepticism. Extraordinary claims need extraordinary evidence. The burden of proof must be high. Right now, we have Mathematical calculations that are probably correct, observations that clearly show something unusual, a debris cloud that is mysteriously absent, and 34 days until better data arrives. That is where we stand. Not, it is definitely aliens. Not, it is definitely natural. Just, the numbers do not match the observations and we need to figure out why. That is honest. That is scientific. That is where the evidence actually leads. If you have watched this entire deep dive nearly 2.5 hours, thank you. Truly, thank you for caring about real science. Thank you for wanting to understand the mathematics. Thank you for being willing to sit with uncertainty instead of demanding easy answers. This is how discovery happens. Not in dramatic eureka moments, but in careful observation, rigorous calculation, and patient waiting for data. We are watching that process unfold in real time. Here is what you can do next. Subscribe and turn on notifications, because when December observations arrive, I will break them down immediately. Every detail, every implication, what it means. Like this video if you found it valuable. It tells the algorithm that people want depth, accuracy, and real scientific exploration. Share it with anyone curious about 3i Atlas, because the more people watching, the harder it becomes for anomalies to be dismissed. And comment below with your prediction. Do you think the debris cloud is out there, too faint to see? Do you think the calculations overestimate the mass loss? Or do you think this comet is doing something no natural comet should be able to do? I genuinely want to know. The final thought? 5 billion tons. Possibly 50 billion tons. That is not speculation. That is conservation of momentum, the physics that guides spacecraft, launches satellites, and has never once failed when applied correctly. If those tons were ejected, they should be somewhere. If they are not, something is deeply wrong with our observations, or with our understanding of comet physics. December will tell us which. Until then, 3i Atlas keeps its secret. An ancient wanderer from another star, carrying ice that formed more than 10 billion years ago, drifting through our solar system for a brief moment, before sinking back into the endless darkness between the stars, whole, intact, impossible, defying the mathematics that say it should have torn itself apart. And we watch, and we measure, and we wonder, because the universe does not care what we think should happen. It only cares what does happen. And sometimes, just sometimes, what happens is something we never imagined was possible. Clear skies, everyone. December 19th is coming, and whatever comes with it, we are about to find out.